Look up at the night sky on a clear, dark evening. Far from the city lights, you can see a faint, shimmering river of stars stretching overhead our own Milky Way galaxy. It's a sight that has captivated humanity for millennia, a canvas of quiet, constant light. But with just our eyes, we're only seeing a whisper of what's truly out there. Now, shift your perspective. Imagine we could zoom in, past those familiar stars, through the vast, silent emptiness between galaxies, and bring into focus a single, swirling nebula. A colossal cloud of gas and dust, painted in impossible shades of deep crimson and ethereal blue, where new stars are being born in violent, beautiful processes. It's a place of both creation and mystery, a single question mark written across light years of space. This is the universe as we are just beginning to see it, astonishingly beautiful, overwhelmingly vast, and filled with secrets that defy our understanding. We have built telescopes that can peer back to the dawn of time and sent robotic explorers to distant worlds. We have unraveled the laws of physics and landed on the moon. Yet, for every question we answer, the cosmos seems to present 10 more, each one more profound and puzzling than the last. So, what are the greatest unanswered mysteries of the cosmos? This is not just a list of scientific curiosities. It is a journey to the very edge of human knowledge. We are going to explore the voids in our understanding, the cosmic riddles that keep astronomers and physicists awake at night. These are the questions that challenge our most fundamental ideas about reality itself, from the true nature of the ghostly dark matter holding galaxies together to the baffling possibility of what, or who else might be out there in the immense silence. This is an invitation to wonder, to stand at the frontier and look into the darkness, not with fear, but with a shared, burning curiosity. Get ready to explore the enigmas that define our place in the universe, the profound puzzles that remind us that the greatest adventure of discovery is still, and always, just beginning. And so, we arrive at perhaps the most fundamental question of all, one that pushes at the very limits of our comprehension. What happened before the Big Bang? For nearly a century, the Big Bang Theory has stood as our best explanation for the origin and evolution of the cosmos. We have overwhelming evidence that the universe we see today, all the galaxies, stars, and planets, expanded and cooled from an initial state of incredible density and temperature around 13.8 billion years ago. We can trace the cosmic expansion back, like a movie in reverse, watching galaxies crowd together, the universe getting hotter and denser until we reach a point where our current understanding of physics simply stops working. This is the singularity, a point of infinite density where the known laws of gravity and quantum mechanics fall apart. It's the ultimate edge of our scientific map, a place where the tools we use to describe reality become useless. Think of it like trying to use a standard weather map to describe the conditions at the very eye of a hurricane. The rules are different there. Our conventional instruments can't give us a reading. This period, right at the very beginning, is often called the Planck epoch, a fleeting fraction of a second after the Big Bang where the universe was so unimaginably hot and dense that all the fundamental forces of nature were likely unified into a single super force. But what about before that? What about the moment of the Big Bang itself and the time that might have preceded it? Our concept of before might not even apply because according to our best models, time itself began with the Big Bang. Asking what happened before the Big Bang could be like asking what is north of the North Pole. The question, in the framework we have, might be meaningless. Yet, the human mind is not so easily satisfied. We are compelled to look beyond that veil, Scientists have proposed several fascinating, albeit highly speculative, ideas to address this profound puzzle. One compelling concept is the cyclic universe model. This theory suggests that our universe is not a one-time event, but part of an endless cycle of expansion and contraction. In this view, what we call the Big Bang was not the absolute beginning, but rather a big bounce, a moment when a previous universe collapsed in a big crunch and then rebounded, giving birth to our own cosmic epoch. In this eternal cycle, there is no true beginning or end, just an endless cosmic rhythm of birth, death, and rebirth. Another mind-bending proposal comes from quantum mechanics, which tells us that empty space is not truly empty, but is a seething foam of virtual particles popping in and out of existence. Perhaps our entire universe is the result of a random, colossal quantum fluctuation in a pre-existing nothingness, a fluctuation that somehow stabilized and inflated into the vast cosmos we inhabit. These theories are not just wild guesses. They are mathematically rigorous attempts to peer beyond the singularity where our current physics fails. They represent the courageous effort of science to explore the ultimate question of origins, to ask what, if anything, came before the dawn of our time and space. It's a mystery that lies at the very heart of existence, a silent question mark hanging over the moment of creation itself. Having pondered the unknowable moment of our cosmic beginning, we are pulled forward by an equally compelling question, one that looks not to the past, but to the distant, distant future. What is the ultimate fate of the universe? Depending on the nature of a mysterious force we are only just beginning to comprehend, the final chapter of the cosmos could be one of icy silence, violent disintegration, or a dramatic reversal back to its origins. For a long time, scientists believed this destiny was a simple tug of war between two opponents: the initial momentum of the Big Bang, which is still pushing galaxies apart, and the relentless inward pull of gravity, working to bring everything back together. The winner of this cosmic contest would determine everything. But in the late 1990s, astronomers made a startling discovery that completely upended this straightforward picture. They found that the expansion of the universe is not slowing down as expected due to gravity. It is actually speeding up. Some unknown repulsive force, which we now call dark energy, is overpowering gravity and driving the galaxies apart at an ever-increasing rate. The ultimate fate of everything now hinges on the precise character of this mysterious dark energy. And right now, we have no definitive idea what it truly is. This deep uncertainty gives rise to several possible endings for our universe. The leading scenario, based on our current best measurements, is often called the Big Freeze or heat death. In this future, dark energy continues to dominate, and the expansion of the universe continues forever, accelerating into an endless, runaway stretch. Over trillions upon trillions of years, galaxies will drift apart until every star in every galaxy has burned out, their fuel exhausted. Black holes will slowly evaporate over almost unimaginable timescales, and the universe will gradually cool toward absolute zero, a state of maximum entropy where no energy is available to do any work. It becomes a vast, dark, and incredibly dilute sea of fundamental particles, where the occasional photon drifts through an endless, frigid emptiness. It is a quiet, slow, and profoundly lonely end, a final state of equilibrium where all cosmic activity and structure simply fade into a uniform, featureless darkness. But what if dark energy is not constant? What if its repulsive strength actually increases over time? This possibility leads to a far more dramatic and violent finale known as the Big Rip. In this scenario, The accelerating expansion doesn't just push galaxies apart. It becomes so powerful that it overwhelms every single force that holds things together. First, the gravitational bonds between galaxy clusters would be severed. Then, individual galaxies would be torn apart. As the force intensifies, it would rip stars from their galaxies and planets from their stars. In the final, terrifying moments before the end, the repulsive force would grow so strong that it would overcome the forces holding atoms together. Molecules, then atoms themselves, and finally atomic nuclei would be violently shredded apart. The universe would dissolve into a soup of disconnected fundamental particles, unable to ever interact again. The very fabric of space-time would be torn asunder. This is an end not of cold and quiet, but of ultimate, unstoppable disintegration. There remains a third, more cyclical possibility, the Big Crunch. This was the original hypothetical end before dark energy was discovered. In this model, the density of matter and energy in the universe is high enough that, eventually, the collective pull of gravity will overcome the expansion. The universe would slow its outward flight, pause, and then begin to collapse inward upon itself. Galaxies would start rushing toward each other. The background temperature of the universe would rise, and the sky would glow hotter and brighter. In the final moments, everything we know, every galaxy, every star, every planet, every atom, would be compressed together into an incredibly hot, dense state, potentially a new singularity. Some theories even suggest this singularity could trigger another Big Bang, giving rise to a brand new universe in an endless cycle of cosmic death and rebirth. While current evidence makes this seem less likely, it remains a captivating idea that offers a kind of cosmic renewal instead of a final end. So, which of these destinies awaits us? The answer lies in precisely measuring the properties of dark energy, and that is one of the most active and challenging frontiers in all of science. Is dark energy constant, as Einstein's cosmological constant suggested? Or is it a dynamic field that can change, a concept sometimes called quintessence? The difference is subtle, but its implications for the far future are total. We are left with a profound realization: the ultimate fate of the entire cosmos, a story spanning hundreds of billions of years, depends entirely on the nature of a ghostly, invisible force that we have only just confirmed exists. It is a humbling reminder that our understanding of the universe is still in its infancy, and that the final page of the cosmic story remains unwritten. We have looked to the beginning and the possible end of all things, but to understand the universe we live in now, we must confront its most dominant yet invisible component. The stars, planets, and galaxies we see glittering in the void make up less than 5% of the total content of the cosmos. The rest is a profound mystery, a darkness we cannot see. For nearly a century, evidence has been mounting that the vast majority of matter in the universe does not emit, absorb, or reflect any light. It is completely transparent, yet it exerts a powerful gravitational pull on everything we can see. This is the enigma of dark matter. The first major clue came from the way galaxies spin. Our own Milky Way, and every other spiral galaxy we observe, rotates at such a tremendous speed that it should be flying apart. The stars on the outer edges are whipping around so fast that the gravity from all the visible stars, gas, and dust in the galaxy is not nearly strong enough to hold them in orbit. It is as if you were watching a child on a playground merry-go-round, spinning so rapidly that the centrifugal force should fling them off into the distance. But they aren't flying away. They are held on by some unseen hand. For galaxies, That hand is the immense gravitational grip of a huge, massive halo of dark matter that envelops the entire galaxy, providing the extra gravity needed to keep it all together. Without this invisible anchor, galaxies like our own would have never formed, and the stars we see at night would have been scattered across the cosmos long ago. Another stunning piece of evidence comes from a phenomenon predicted by Einstein's theory of general relativity: gravitational lensing. Massive objects warp the fabric of space-time around them, bending the path of light that travels past, just like a lens in a magnifying glass. Astronomers can observe distant galaxies whose light is distorted and warped as it passes through a massive galaxy cluster on its way to our telescopes. By carefully measuring the amount of this distortion, scientists can calculate the total mass of the galaxy cluster causing the lensing. Time and again, the result is the same. The mass required to create the observed bending of light is many times greater than the mass of all the visible matter in that cluster. There is a tremendous amount of something else there, something we cannot see, providing the bulk of the gravitational muscle. So we know dark matter is real. We can map its distribution across the universe. We know it forms the cosmic scaffolding upon which galaxies are built, but we have no idea what it is made of. It is not made of atoms, not the protons, neutrons, and electrons that constitute everything you have ever touched or seen. It must be something entirely new, a fundamental particle that does not interact with the electromagnetic force, which is why it is completely dark. The search to identify this particle is one of the most intense efforts in modern physics. The leading theoretical candidate for decades has been the WIMP, or weakly interacting massive particle. As the name suggests, these are hypothetical particles that have mass and therefore feel gravity, but they interact with normal matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. Scientists have built exquisitely sensitive detectors, often placed deep underground in old mines to shield them from cosmic rays, hoping to catch the rare, faint bump of a WIMP colliding with an atom of normal matter. After decades of searching, these detectors have remained silent. This lack of a direct detection has spurred interest in other candidates, such as the action. Actions are hypothetical particles that were originally proposed to solve a different, arcane problem in particle physics, but they also have the right properties to be a dark matter component. They would be incredibly light, potentially billions of times lighter than an electron, and would flood the universe in a vast, cold wave. Experiments are now being built to try and convert these ghostly actions into detectable photons using powerful magnetic fields. Meanwhile, physicists are also using powerful machines like the Large Hadron Collider to try and create dark matter particles by smashing normal particles together at nearly the speed of light. The hope is that in the tremendous energy of these collisions, we might briefly create something from the dark sector and observe the telltale missing energy it carries away. So far, no definitive signal has emerged. We are surrounded by this mysterious substance, feeling its gravitational influence on the largest scales, yet it continues to elude our every attempt to grasp its true nature. It is the ghost in the cosmic machine, a silent partner in the evolution of the universe whose identity remains one of science's greatest puzzles. If dark matter is the invisible cosmic glue holding galaxies together, then dark energy is its polar opposite, a mysterious, repulsive force that is tearing the cosmos apart on the grandest of scales. This discovery, which earned the Nobel Prize in Physics in 2011, was one of the most shocking in the history of science. two independent teams of astronomers were studying distant stellar explosions called Type 1a supernova, which are used as standard candles to measure cosmic distances. They expected to find that the expansion of the universe was slowing down over time, as the collective gravity of all the matter in the cosmos pulled back on the initial momentum of the Big Bang. Instead, they found the opposite. The most distant supernova were fainter than predicted, meaning they were farther away than they should have been. The inescapable conclusion was that the expansion of the universe is not slowing down. It is accelerating. Something is actively pushing galaxies away from each other, and that something is what we now call dark energy. To understand the sheer dominance of this force, consider the cosmic budget of the universe. All the ordinary matter that makes up stars, planets, and us, the stuff of the periodic table, accounts for a paltry 5% of the total cosmos. Dark matter, the gravitational anchor, makes up about 27%. The remaining 68%, the overwhelming majority of everything, is dark energy. This means the fate of our universe is not being dictated by the stuff we can see and feel, but by this enigmatic, repulsive pressure inherent in the fabric of space itself. While dark matter works to pull structures together through gravity, dark energy works on the empty voids between galaxy clusters, causing space itself to stretch and driving those clusters apart at a rate that increases with every passing moment. The leading explanation for dark energy is a concept that dates back to Albert Einstein himself, the cosmological constant. When Einstein was developing his theory of general relativity, his equations suggested the universe should be either expanding or contracting. Believing at the time in a static, unchanging cosmos, he introduced a fudge factor, a repulsive force that would counterbalance gravity on the largest scales to keep the universe stable. He later called this his greatest blunder after Edwin Hubble discovered the universe was indeed expanding. Yet, with the discovery of the accelerating expansion, the cosmological constant was resurrected. In this modern view, it represents the energy density of the vacuum of space itself. According to quantum physics, empty space is not truly empty. It is a seething, bubbling foam of virtual particles that constantly flicker in and out of existence. This vacuum energy should produce a repulsive gravitational effect, acting as the cosmological constant and driving the acceleration we observe. This leads directly to one of the most profound and unsettling problems in all of theoretical physics, the cosmological constant problem. When physicists attempt to calculate the theoretical value of this vacuum energy using quantum field theory, the number they get is absurdly, impossibly large. We're not talking about a small discrepancy. The predicted value is about 120 orders of magnitude. That's a 1 with 120 zeros after it, greater than the value we actually observe from cosmic acceleration. This is the single worst prediction in the entire history of science. It suggests that our understanding of the quantum vacuum and gravity on cosmological scales is fundamentally incomplete or broken. Some physicists have described this as a crisis that points toward the need for a revolutionary new theory, perhaps one that successfully unites gravity with quantum mechanics. So we are left with a staggering paradox. We have observed the effects of dark energy with high certainty, and the cosmological constant is the simplest fit to the data. Yet, our best theories cannot explain why its strength is so vanishingly weak compared to what we would expect. If the theoretical prediction were correct, the repulsive force would have been so immense that it would have blown the universe apart in the first instant of the Big Bang, preventing any stars, galaxies, or life from ever forming. The fact that we exist to ponder this question at all means the value must be incredibly fine-tuned. This has led some to propose alternative ideas, such as quintessence, a dynamic energy field that changes over time, unlike the constant vacuum energy. If quintessence is real, the accelerated expansion might not continue forever. It could potentially slow down or even reverse in the far future. However, current observational evidence still strongly favors the simple cosmological constant, leaving us to grapple with its deeply puzzling implications. We have identified the force that controls the ultimate destiny of the cosmos, but its true nature remains an impenetrable secret, hidden within the empty space that surrounds us all. From the invisible forces shaping the cosmos, we now turn to a question that strikes at the very heart of our own existence and significance. Given the sheer scale of the universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, many with orbiting planets, the numbers alone suggest that life should be commonplace. The chemistry of life is based on universal elements like carbon, and we find the building blocks of life, amino acids, on asteroids and in the vast clouds of interstellar space. It seems almost statistically inevitable that life has arisen elsewhere. This line of thinking led physicist Enrico Fermi, during a casual lunch conversation in 1950, to pose a now famous and deeply unsettling question. If life is so probable, and the galaxy is so old, then where is everybody? Why do we see no signs, no artifacts, no signals, no visitors? This is the Fermi paradox, the profound contradiction between the high estimated probability of extraterrestrial civilizations and the utter lack of evidence for them. To frame this probability, astronomer Frank Drake proposed an equation, not to find a single answer, but to break down the problem into manageable factors. The Drake equation multiplies a series of variables: the rate of star formation, the fraction of stars with planets, the number of planets in each system that could potentially support life, the fraction of those where life actually emerges, the fraction where that life becomes intelligent, the fraction that developed technology that releases detectable signs into space, and finally, the length of time such civilizations remain detectable. Plug in optimistic numbers that life develops easily and intelligent. Technological civilizations are common, and you get a galaxy teeming with life, with thousands or even millions of civilizations. Yet, when we listen with our radio telescopes or look with our most powerful instruments, we are met with a profound and echoing silence. This silence is the core of the paradox, and it has generated a spectrum of possible solutions, some comforting and others deeply sobering. One of the most compelling explanations is the concept of the Great Filter. This hypothesis suggests that there exists some kind of barrier, an evolutionary or technological challenge so difficult that virtually no life can overcome it. The Great Filter could lie in our past, a step that we, against all odds, managed to pass. Perhaps the origin of life itself from non-living chemistry is an astronomically rare event. Or maybe the jump from simple prokaryotic cells to complex eukaryotic cells, which took over 1 billion years on Earth, is the true bottleneck. If this is the case, then the filter is behind us, and we might be among the first, or even the only technologically advanced civilization in our galaxy. This is an optimistic view for humanity's future potential. The more unsettling possibility is that the Great Filter lies in our future. Perhaps there is some inevitable calamity that befalls all advanced civilizations once they reach a certain level of technological development. It could be self-destruction through nuclear war or engineered pandemics, or an external threat like a runaway artificial intelligence that eliminates its creators, or perhaps a natural cosmic disaster, like gamma-ray bursts, that regularly sterilizes galaxies. If this future filter exists, then our continued existence is not guaranteed, and the silence of the cosmos is a grim warning of a fate that awaits all who reach our stage of development. Other solutions to the paradox are less apocalyptic but still place profound limitations on interstellar life and travel. The vast distances between stars and the incredible amounts of energy and time required to cross them might simply make physical travel impractical for any civilization. The laws of physics, as we understand them, present a formidable barrier. Alternatively, we might be looking for the wrong things. Our searches largely focus on radio signals, a technology we have used for barely a century. A civilization just a few thousand years more advanced than us might use forms of communication we cannot even conceive of, like neutrino messaging or quantum entanglement, which would be completely invisible to our current detectors. They could be all around us, swimming in a sea of information we lack the senses to perceive. Another fascinating idea is the zoo hypothesis or the planetarium hypothesis. This suggests that advanced civilizations are aware of us, but have chosen to isolate us, much like we set aside a nature preserve. They might be observing our cultural and technological development without interference, adhering to a form of galactic non-interference protocol. Or they might have the technological capability to project a perfect simulation of a silent, empty universe around our solar system, a cosmic planetarium designed to hide their presence entirely. Perhaps the universe we perceive is actively being curated to appear barren. Then there is the deeply humbling possibility that we are simply not interesting enough, or that the timescales are mismatched. The universe is 13.8 billion years old. A civilization that became interstellar just a few million years before us would be so far beyond our comprehension that we might be like ants trying to comprehend human global politics. Their activities might be on such a vast scale or utilize such advanced physics that we are oblivious to them. They could be harnessing the energy of entire stars with Dyson spheres, structures we are only beginning to theorize how to look for, or they may have transcended biological form entirely, existing as post-biological intelligences in unimaginable states. The silence we hear may not be the silence of absence, but the silence of a cosmos occupied by entities whose motives and methods are so alien that we simply do not know how to see them. The Fermi paradox forces us to confront not only the possibility of other life, but the very nature of intelligence, technology, and the long-term destiny of any civilization that reaches for the stars. This journey from the cosmic to the conscious leads us to one of the most intimate and baffling mysteries of all, one that lies not in the distant reaches of space, but within our own minds. We have explored the vast, dark components of the universe and pondered the silence of the cosmos. But what about the inner universe of subjective experience? What is the nature of consciousness itself? And if it emerged here on Earth, could it exist in other alien forms elsewhere? This is not merely a biological question. It is a fundamental puzzle that bridges neuroscience, philosophy, and the search for extraterrestrial intelligence. At its core is what philosopher David Chalmers termed the hard problem of consciousness. This problem distinguishes between the easy problems understanding which parts of the brain are involved in specific functions like sleep, memory, or attention, and the truly hard problem. Why and how do all these intricate physical and electrochemical processes give rise to subjective, qualitative experience? Why does the processing of visual information in the occipital lobe come with the private, internal sensation of the color red? Why does the firing of neurons in a specific pattern feel like the taste of chocolate or the pang of sadness? We can map the brain in exquisite detail, but we cannot explain how 3 pounds of gelatinous tissue generates the rich, continuous movie of self-aware experience that is your life. This gap between the physical machinery and the inner world is the hard problem, and it remains one of the most significant unsolved questions in science. To grasp the depth of this mystery, consider a simple thought experiment. Imagine a future scientist who knows everything there is to know about the physical processes in a human brain. Every neuron, every synapse, every neurotransmitter. They have a perfect, complete physical description of what is happening when someone sees the color blue. But would that objective, third-person knowledge tell them what it actually feels like from the inside to see blue? It seems there is an unbridgeable gap between the objective description and the subjective experience. This suggests that consciousness may be a fundamental aspect of reality, not just a complex byproduct. Some philosophers and scientists, following in the tradition of panpsychism, propose that consciousness, in some very basic form, is a universal property of matter, much like mass or charge. In this view, even elementary particles might possess a minute degree of subjective experience or proto-consciousness. While this might seem far-fetched, it offers a potential solution. Consciousness didn't emerge from nothing. It was always there, and complex systems like brains simply amplify and unify these fundamental properties into the rich awareness we enjoy. This idea, while highly speculative, radically reshapes our place in the cosmos. If consciousness is fundamental, then the universe is not a cold, empty void, but is in some sense awake, or at least has the potential for wakefulness. This leads directly to a stunning implication for astrobiology. If consciousness is merely a unique, accidental product of human evolution, a quirky side effect of our specific neural wiring, then we might be truly alone in the universe, not just as a technological species, but as experiencing beings. The cosmos would be filled with unconscious, biological automatons or complex but unfeeling machines. However, if consciousness is instead a natural and perhaps even inevitable property of complex information processing, then the universe could be teeming with sentient life in forms we can scarcely imagine. This perspective suggests that anywhere sufficiently complex computation occurs, whether in the neural networks of an alien creature, the distributed intelligence of a silicon-based life form, or even a planetary-scale artificial intelligence, subjective experience could arise. An alien might not have a brain anything like ours. It could be a vast, slow-moving creature that thinks with chemical gradients in a global ocean, or a collective hive mind made of millions of insect-like individuals. Its consciousness would be utterly alien, its experiences unimaginable to us, shaped by entirely different senses and a different relationship to time and space. Yet, if the fundamental link between complex information integration and subjective awareness holds, it would indeed be a conscious entity. This idea is central to the integrated information theory, which proposes that consciousness corresponds to a system's ability to integrate information, and that the quality of that consciousness is determined by the structure of that information network. This possibility forces us to radically reconsider our search for extraterrestrial intelligence. Our current SETI efforts primarily listen for radio signals, a sign of technology. But if we are searching for consciousness, the parameters change. How would we even recognize a non-biological planetary consciousness? What would be the signature of a sentient AI that evolved on another world, its thoughts unfolding over centuries as it orchestrates the climate of its planet? We might be surrounded by conscious entities whose modes of existence and communication are so different from our own that we fail to recognize them as alive, let alone aware. Perhaps a gas giant like Jupiter, with its complex, self-organizing storm systems and immense magnetic fields, hosts a form of slow, atmospheric consciousness entirely beyond our perception. The question of consciousness elsewhere is therefore not just a biological question, but a cosmic one. It challenges our definitions of life, intelligence, and mind. It suggests that the universe might be filled with inner light, with private universes of experience locked within strange and wonderful forms. Yet, without a fundamental theory of how consciousness arises from matter, we are left groping in the dark, unable to even define what we are looking for. The mystery of our own minds becomes the key to unlocking the potential sentience of the cosmos, a profound reminder that the final frontier may not be outer space, but the inner space of being itself. Stepping from the cosmic riddles of mind and matter, we now confront one of the most absolute and terrifying enigmas in the universe. What is inside a black hole? These objects represent the ultimate victory of gravity, regions of space where the gravitational pull is so intense that nothing, not even light, can escape. The boundary that marks this point of no return is called the event horizon. Think of it as a one-way membrane around the black hole. Imagine a canoeist paddling toward a waterfall. There is a critical point in the river where the current becomes so strong that paddling backward is no longer an option. The pull toward the edge is unstoppable. For a black hole, the event horizon is that exact point of no return for space itself. Once any object, a spacecraft, a planet, or a particle of light crosses that invisible threshold, its fate is sealed. It is pulled inexorably toward the center, and from our perspective outside, we would never see it actually cross. Due to the extreme warping of time predicted by Einstein's relativity, an object falling in would appear to slow down, becoming redder and dimmer until it fades from view entirely, its image frozen for all eternity on the event horizon's surface. But what happens after that fateful crossing? Our current laws of physics give us a clear prediction, but it is one that signals their own complete breakdown. According to general relativity, all the matter that falls through the event horizon is crushed into an infinitely small, infinitely dense point at the very center, known as the singularity. Here, the curvature of space-time becomes infinite, and the concepts of space and time as we know them cease to have any meaning. Our reliable equations of gravity simply output nonsense division by zero, infinities telling us that our understanding of reality is fundamentally incomplete. The singularity is a place where the rulebook of the universe burns to ash, a mathematical warning that a deeper theory, one that successfully merges gravity with quantum mechanics, is needed to describe what truly occurs. This confrontation between gravity and quantum theory ignites one of the most heated debates in modern physics, centered on a puzzle known as the black hole information paradox. Quantum mechanics, the rules governing the subatomic world, is built on a fundamental principle: information is never truly lost. If you burn a book, the information in its pages seems destroyed, but in principle, if you could collect every single smoke particle and trace every photon of heat emitted, you could theoretically reconstruct the entire book. The information is scrambled, but it is conserved. Black holes, however, appear to shatter this sacred principle. When an object falls into a black hole, it carries all its information with it, the specific arrangement of particles that made it a star, a planet, or a library. If the black hole then slowly evaporates over eons through a process called Hawking radiation, which theory suggests is a featureless glow of random particles. What happens to that original information? If the Hawking radiation contains no trace of the information about what fell in, then when the black hole finally vanishes, that information is erased from the universe forever. This presents a stark either-or choice. Either our understanding of quantum mechanics is wrong, or our understanding of black holes and gravity is wrong. Something has to give. This paradox has forced physicists to propose some truly mind-bending solutions. One of the most profound is the holographic principle. This idea suggests that all the information about everything that has ever fallen into a black hole is not lost inside, but is instead encoded on a two-dimensional surface, the event horizon itself, like a cosmic hard drive. In this view, the three-dimensional space we perceive inside the black hole is a projection of this information, much like a three-dimensional hologram is projected from a two-dimensional film. The universe, at its most fundamental level, might be a vast, complex hologram. If this is true, then information is never truly inside the singularity. It is smeared across the boundary, preserved forever even as the black hole evaporates. Another drastic proposal to resolve the paradox is the concept of the black hole firewall. Imagine an astronaut foolishly crossing the event horizon. According to classical relativity, they should feel nothing special at that moment. The event horizon is locally just empty space. But the firewall hypothesis suggests that this peaceful picture is an illusion. To protect the law of information conservation, a searing wall of ultra-high energy particles might exist just inside the event horizon, an invisible barrier of pure fury that would instantly incinerate anything falling in. In this scenario, information is not lost because anything carrying it is vaporized at the firewall, and its information is imprinted onto the Hawking radiation being emitted outward. While this saves quantum mechanics, it does so by dramatically violating Einstein's principle that free fall through the event horizon should be uneventful. The debate between these ideas, the holographic universe and the violent firewall, highlights the sheer strangeness of the problem. We are grappling with the fundamental laws of reality at their breaking point, and the true nature of a black hole's interior remains one of the most compelling and unresolved frontiers in all of science. Yet another mind-bending implication of Einstein's theory of general relativity is the theoretical possibility of wormholes, cosmic shortcuts tunneling through the very fabric of spacetime. Imagine the universe not as a flat sheet, but as a vast, multi-dimensional loaf of bread. To get from one crumb on the top crust to another crumb on the bottom, an ant would have to traverse the entire length of the loaf. But what if the ant could instead burrow a hole directly through the soft interior, creating a much shorter path? A wormhole, or Einstein-Rosen bridge, is precisely that, a tunnel connecting two distant points in space, or even two different points in time, creating a bridge that could potentially reduce a journey of millions of light years to a mere stroll across a threshold. The mathematics of general relativity allows for such structures, describing them as a warping of spacetime that forms two mouths connected by a throat. For a moment, it sounds like the ultimate key to the cosmos, a way to bypass the immense, isolating distances between stars and make interstellar exploration a tangible reality. But the devil, as always, is in the details, and the details of wormholes are where the dream crashes into formidable physical reality. The single greatest obstacle to a stable, traversable wormhole is its inherent instability. According to the equations, the throat of a wormhole would want to collapse into a singularity faster than the speed of light, pinching shut instantly. Anything attempting to enter would be crushed out of existence in a fraction of a second. To keep this tunnel propped open, you would need a form of material with truly bizarre properties, something that exerts negative energy density, or in simpler terms, negative gravity. This is what physicists call exotic matter. Unlike anything we have ever encountered, this substance would have to gravitationally repel rather than attract. It would be the ultimate scaffolding, pushing the walls of the wormhole apart against their immense tendency to collapse. The problem is, we have no proof that such exotic matter exists in the quantities required. In the quantum world, there are hints of similar phenomena, like the Casimir effect, where the energy density between two closely spaced metal plates in a vacuum can be measured as slightly negative. But the amount of exotic matter needed to stabilize a wormhole large enough for a single atom to pass through is astronomical, let alone one for a spaceship. We are talking about quantities of this hypothetical substance equivalent to the mass energy of an entire star, all configured in a perfect, stable shell. This is a monumental engineering challenge that lies so far beyond our current capabilities, it might as well be magic. This leads to a profound question. Are wormholes merely mathematical phantoms in our most elegant equations, or could they be real, natural features of the cosmos? Some theoretical physicists speculate that the universe might be threaded with primordial wormholes, tiny tunnels woven into the very fabric of space-time during the Big Bang. These would be microscopic, perhaps existing at the Planck scale, far smaller than an atom. If they do exist, and if they could be somehow located, captured, and inflated to a usable size using unimaginable amounts of energy and exotic matter, then the possibility of travel opens up. But this is a chain of increasingly speculative ifs. Another chilling consideration is that wormholes don't just offer shortcuts through space. They are also potential time machines. If one mouth of the wormhole were moved at a significant fraction of light speed or placed in a powerful gravitational field, time would pass more slowly for it relative to the other, stationary mouth, as predicted by relativity. After such a journey, the two ends would be connected not just by space, but by time. Stepping into one mouth could mean stepping out of the other, not just in a different location, but in a different century, perhaps the deep past. This immediately raises the classic time travel paradoxes, like the grandfather paradox, where you could potentially prevent your own existence. The laws of physics, as we understand them, seem to abhor such paradoxes, which leads many physicists to propose mechanisms, like the chronology protection conjecture, that would prevent the formation of such closed time-like curves, effectively making time travel to the past impossible. The universe may have built-in safeguards to protect history from contradiction. So, while the concept of wormholes captures our imagination and fuels our science fiction dreams, they remain firmly in the realm of theoretical possibility. They are a dazzling consequence of our best theory of gravity, a testament to the strange and wonderful universe general relativity describes. Yet, they are also a stark reminder of the chasm between what is mathematically possible and what is physically attainable. The dream of stepping through a gateway to another star system or another time is one of the most compelling in all of science, but it is a dream that, for now, is held shut by the crushing weight of physics itself. The idea that our universe might be just one of countless others is one of the most staggering propositions in all of modern cosmology. We've journeyed through black holes and wrestled with the nature of consciousness, but this concept, known as the multiverse, challenges the very definition of reality itself. It suggests that everything we can observe, every galaxy, every star, every one of us, is just a single specimen in an infinite cosmic collection. This isn't merely a philosophical thought experiment. It emerges as a potential consequence of our most successful theories in physics, particularly the theory of cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the fabric of space-time underwent a period of exponential, faster-than-light expansion, smoothing out the universe and planting the seeds for all future structure. But a compelling extension of this idea, called eternal inflation, suggests that this explosive expansion didn't stop everywhere at once. Instead, it stopped in our local patch, creating what we call our observable universe, but it continues unabated in a vast, overarching background. In this eternal sea of inflating space, new bubble universes are constantly budding off, each one a self-contained cosmos with its own Big Bang and its own potentially unique properties. In this Level 2 inflationary multiverse, the number of these bubble universes isn't just large, it's truly infinite, a never-ending froth of cosmic realms being born forever. Stepping away from the grand cosmic landscape, another version of the multiverse emerges from the bizarre and counterintuitive world of the very small. According to the standard Copenhagen interpretation of quantum mechanics, particles exist in a haze of probability until the moment they are observed, at which point their wave function collapses into a single definite state. But the many worlds interpretation proposed by Hugh Everett in the 1950s offers a radically different and mind-bending alternative. It suggests that the wave function never collapses. Instead, every time a quantum event has multiple possible outcomes, the entire universe splits into branches, each one realizing a different possibility. In this Level 3 multiverse, every choice, every random quantum decay, every chance event that could have happened, does happen in some alternate reality. There's a universe where you decided to wear a different color shirt today, and another where a key cosmic ray missed a DNA molecule in your distant ancestor, preventing your lineage altogether. This isn't about traveling to other galaxies. It's about a near infinite stack of realities diverging from our own, all equally real, and all existing in a vast, ever-branching tree of quantum possibility. What gives the multiverse concept such profound weight is the implication that these other realms are not just copies of our own. They could be realms where the very rules of the game are completely different. Our universe seems curiously fine-tuned for life. If the strength of the force that binds atomic nuclei were even slightly stronger or weaker, stars would either burn out in an instant or never form at all. If the amount of dark energy were marginally greater, the universe would have blown apart before galaxies could coalesce. This fine-tuning problem has long puzzled scientists and theologians alike. The multiverse offers a potential scientific explanation. If there are an infinite number of universes, each with randomly set physical constants, then it's no surprise that we find ourselves in one of the rare, incredibly unlikely universes where the constants are just right for atoms, stars, planets, and ultimately, life to exist. We are not the product of a miraculous, one-time tuning. We are simply the inevitable inhabitants of a universe that permits us to be here. In the vast majority of other bubbles, the laws of physics might be so alien that matter is unstable, or gravity is repulsive, or time runs backward. Those universes would be stillborn, empty, or utterly incomprehensible to us. Yet, for all its compelling explanatory power, the multiverse remains one of the most hotly debated ideas in science, primarily because of one enormous challenge: testability. The core principle of the scientific method is that an idea must make predictions that can be, at least in principle, falsified by observation or experiment. But if these other universes are causally disconnected from our own, existing beyond our cosmic horizon in either space or a separate quantum branch, how could we ever detect them? Any potential evidence is indirect and highly speculative. Some theorists suggest that if our universe had collided with another bubble universe in the distant past, it might have left an imprint on the cosmic microwave background radiation, a sort of bruise on the fabric of our cosmos. We've looked for such anomalies, but none have been conclusively found. Others propose that the peculiar nature of dark energy might be a clue, a subtle influence from adjacent universes in the wider multiversal landscape. Without a direct method of verification, critics argue that the multiverse is not science, but rather a metaphysical speculation, a philosophical placeholder for our ignorance that risks halting the search for a deeper, single universe theory that could explain our fine-tuning without resorting to an infinity of unseen worlds. This debate strikes at the very heart of what science is and what its limits might be. Are we in a universe that may be infinite in extent and potential, forever limited to exploring just our own local neighborhood? The multiverse dares us to consider that the totality of reality may be far grander and more mysterious than we ever dreamed, even if its full scope remains, for now, tantalizingly out of reach. Building on this idea of a potentially infinite cosmic landscape, we are driven to ask a more fundamental question about the space we actually inhabit. What is the true size and shape of the universe? We often hear that the universe is expanding, but into what? And does it even have an edge? To begin, we must make a crucial distinction between what we can see and what might actually be out there. The part we can study is called the observable universe. Think of yourself standing in the middle of a vast, dense fog. You can only see a finite distance in every direction before the fog obscures your view. That sphere of visibility is your personal observable universe. For us, the fog is not made of water vapor, but of time itself. Because the universe has a finite age, about 13.8 billion years, and because light travels at a finite speed, we can only receive light from objects whose light has had enough time to reach us. This creates a cosmic horizon, a boundary beyond which we cannot see, not because there's nothing there, but because the light from those more distant regions hasn't reached us yet, and may never will do to the accelerating expansion. The observable universe is therefore a sphere centered on us, with a radius of about 46.5 billion light-years. It contains all the galaxies, stars, and cosmic background radiation that we can possibly detect. But this is just our local neighborhood. It is almost certainly not the whole story, what lies beyond our cosmic horizon. This is where the question of the universe's true, global nature comes into play, and there are two primary, staggering possibilities. The first is that the universe is finite. It has a limited volume, much like the Earth has a finite surface area. If this is the case, then if you could build a spacecraft that traveled in a perfectly straight line for an impossibly long time, you would eventually return to your starting point from the opposite direction, without ever encountering a wall or an edge. This is the concept of a finite but unbounded universe. The most common analogy for this is the surface of a balloon. As you inflate it, the two-dimensional surface area expands, and any ants living on that surface would see all other ants moving away from them. The surface has no boundary. An ant can walk forever in one direction and never fall off, yet the total area is clearly finite. In 3 dimensions, a finite universe could have a similar, more complex shape, like a hypersphere. The other, perhaps more mind-boggling possibility is that the universe is truly infinite. In this scenario, space just goes on forever. Beyond our observable horizon, there are more galaxies, stars, and planets, continuing without end. The number of stars, and potentially the number of planets with life, would be literally infinite. Both ideas are deeply unsettling in their own way. One places us in a contained, cosmic fishbowl, while the other places us in a reality of limitless and perhaps redundant existence. So how do we possibly determine which of these is correct? We cannot travel to the edge, so we must rely on measuring the geometry of the universe. According to Einstein's theory of general relativity, the overall shape of the cosmos is determined by its total mass and energy density. This leads to three potential geometries, each with profound implications for its size and fate. The first is a closed geometry, which is positively curved, like the surface of a sphere. In a closed universe, the angles of a very large triangle would add up to more than 180 degrees, and parallel beams of light would eventually converge. This geometry corresponds to a density so high that the universe's own gravity will eventually halt its expansion and cause it to recollapse in a big crunch. A closed universe must be finite. The second is an open geometry, which is negatively curved, like the surface of a saddle. Here, the angles of a triangle add up to less than 180 degrees, and parallel light beams would diverge. An open universe would expand forever, and it is likely, though not certain, to be infinite. The third, and most familiar, is a flat geometry, where the rules of Euclidean geometry we learned in school hold true. The angles of a triangle add up to exactly 180 degrees, and parallel light beams remain parallel. A flat universe has a critical density that perfectly balances the expansion energy, and it, too, would be infinite in extent. For decades, cosmologists have been trying to measure which of these geometries describes our reality, primarily by studying the afterglow of the Big Bang, the cosmic microwave background radiation. This faint glow is the oldest light in the universe, a snapshot from when it was just 380,000 years old. Tiny fluctuations in this background temperature reveal the size of the primordial sound waves that were frozen in place when the universe became transparent. The apparent angular size of these fluctuations on the sky acts as a cosmic ruler. If the universe were positively curved, like a sphere, these imprints would appear larger to us, much like the continents on a globe appear larger than they are on a flat map. If the universe were negatively curved, like a saddle, they would appear smaller. The results from missions like the Planck satellite have been incredibly precise and, for many, surprisingly definitive. The data shows that the universe is flat to within a margin of error of just 0.2%. This extraordinary measurement strongly suggests that our universe, on the largest scales we can measure, has a flat geometry. This finding of flatness has a monumental implication. It points toward an infinite universe. If the cosmos is flat and continues with the same properties beyond our horizon, then it has no boundary and extends forever. This resolves the old puzzle of what the universe is expanding into its not expanding into anything. Infinite space is simply becoming more infinite. However, a crucial caveat remains. While a flat universe is most simply explained by an infinite one, it is also theoretically possible for a flat universe to have a finite size if it has a complex, multiply-connected topology. Imagine a video game world where if you walk off the right edge of the screen, you reappear on the left. In a similar way, a flat universe could be shaped like a torus or a donut, but on a cosmic scale. In such a universe, if you could look far enough, You might see multiple copies of the same galaxy cluster, or even a ghostly image of our own Milky Way from a different direction. Scientists have searched for these telltale repeating patterns in the cosmic microwave background, but so far, none have been found. The silence suggests that if the universe is finite, it is far larger than our observable horizon, or its topology is too complex for us to detect with current technology. So we are left in a profound state of uncertainty. The geometry we can measure is flat, hinting at infinity, but the ultimate size and shape of the entire cosmos remain one of its most deeply hidden secrets, a final frontier that may forever lie just beyond our sight. This brings us to a question that is not just about the cosmos, but about our own existence, a puzzle that asks why there is something rather than nothing. Why is there more matter than antimatter? This is known as the Baryon asymmetry problem, and it stands as one of the most critical missing pieces in our understanding of the universe's origin. The story begins with the Big Bang, which should have been the ultimate act of cosmic symmetry. According to our best models of particle physics, the immense energy of creation should have condensed into particles and antiparticles in perfectly equal amounts. For every quark created, an antiquark should have popped into existence. For every electron, a positron. Matter and antimatter are perfect opposites. When they meet, they annihilate each other in a flash of pure energy, leaving nothing behind. So, in that first fiery moment, the universe should have been a perfectly balanced, seething soup of matter and antimatter, all destined for mutual destruction. After the annihilations were complete, there should have been nothing left but a dilute sea of photons, a universe of light with no material substance, no atoms, no stars, no planets, and certainly no us. The fact that we are here, made of matter, contemplating this very question, is the most glaring evidence that this perfect symmetry was somehow broken. Something happened in the early universe that created a tiny, 1 in a billion surplus of matter over antimatter. The quest to find the source of this imbalance takes us into the heart of the subatomic world and a set of conditions known as the Sakharov conditions, named after the physicist Andrei Sakharov. He outlined 3 essential criteria that must be met for a matter-dominated universe to emerge. First, there must be a process that violates the conservation of Baryon number, a rule that essentially says the total amount of matter in the universe should stay constant. Second, the laws of physics must treat particles and antiparticles differently, a phenomenon known as CP violation. And third, this all had to occur out of thermal equilibrium, meaning it couldn't happen in a calm, settled environment, but rather during a rapid, dramatic phase transition in the hot, early cosmos. The smoking gun in this cosmic detective story has been the search for CP violation. The C stands for charge conjugation, which means swapping a particle for its antiparticle. The P stands for parity, which is like looking at a particle in a mirror. For a long time, physicists believed that the laws of physics were perfectly symmetric under a CP transformation. That is, a process involving particles should look identical to the mirror image process involving antiparticles. If this were true, matter and antimatter would have behaved in lockstep, leading to total annihilation. The discovery of CP violation in 1964 was therefore a monumental breakthrough. Scientists studying the decay of neutral K mesons found that the matter and antimatter versions of these particles decayed at slightly different rates. This was the first concrete proof that nature itself has a tiny, built-in preference for matter over antimatter. The problem, however, is one of scale. The amount of CP violation we have observed in laboratory experiments is pathetically small. far too feeble to account for the overwhelming dominance of matter in our universe. The imbalance we see in experiments is only about 1 part in a billion, while to produce the cosmic structure we observe, the initial asymmetry needed to be just 1 part in 10 billion. We are off by a factor of 10. This means the known sources of CP violation in the standard model of particle physics are insufficient to save the universe from total annihilation. It's as if we found a single drop of water that could explain a small puddle, but we need an entire ocean to explain the reality we see. This glaring shortfall tells physicists that there must be other, much stronger sources of CP violation out there, lurking in physics beyond our current standard model. The search for this new physics is intense and multifaceted. One of the primary arenas for this hunt is the study of neutrinos. These ghostly particles, which barely interact with matter, might be their own antiparticles, a class of particles known as Majorana fermions. If this is true, a rare nuclear process called neutrinoless double beta decay could occur, which would be a dramatic violation of lepton number, another key piece of the puzzle. Experiments deep underground are tirelessly searching for the faintest signature of this process. Another promising avenue involves the elusive beauty quark. The LHCb experiment at the Large Hadron Collider is meticulously measuring the decay rates of particles containing beauty quarks and their antimatter counterparts, hunting for any subtle differences that could reveal a new, much stronger source of CP violation. Every tiny discrepancy from the predictions of the standard model is a potential clue, a signpost pointing toward the new physics that tipped the cosmic scales in our favor. The implications of this search are as profound as they get. Solving the mystery of baryon asymmetry would not only explain our existence, but would also provide a direct window into the fundamental laws of nature at energies we can never hope to recreate in a laboratory. It was a process that occurred in the first fleeting fractions of a second after the Big Bang, during an era of unimaginable energy. By understanding the mechanism that saved 1 extra matter particle out of every 10 billion annihilations, we would be glimpsing the very engine of creation. This isn't just a minor detail in cosmology. It is the reason anything at all, the galaxies, the stars, the Earth, and every one of us, is here to ponder the universe. The fact that we exist is the ultimate clue that the early universe was not perfectly symmetrical, and our continued search for the reason why is one of the most profound quests in all of science. From the immense scales of cosmic creation and annihilation, we now turn our attention to a relentless, invisible rain that constantly bombards our planet from the deepest reaches of space. They are cosmic rays, and among them exist particles so energetic, so utterly powerful, that they defy our comprehension and our ability to explain them. These are ultra-high-energy cosmic rays, and they carry more kinetic energy than a professionally thrown baseball, all compressed into a single subatomic particle. Imagine a proton, one of the tiny building blocks of an atom, traveling through space at a speed just a whisper below the speed of light, carrying with it the punch of 100 million billion electron volts. To put that into perspective, that is millions of times more energy than the most powerful collisions we can create here on Earth with our largest machine, the Large Hadron Collider. Nature is flinging these microscopic cannonballs at us, and we have no earthly idea how it's possible. The existence of these particles presents a monumental puzzle, one that astrophysicists have been trying to solve for decades. Where do these unimaginable accelerators exist? And what physical processes could possibly be powerful enough to launch a single particle with such ferocious force? The first and perhaps greatest challenge in this cosmic detective story is simply tracing these particles back to their source. Unlike light, which travels in a straight line from its origin, cosmic rays are charged particles, mostly protons and atomic nuclei. As they journey across the vast, magnetized expanse of interstellar and intergalactic space, their paths are twisted and bent by magnetic fields. Think of it like trying to trace the path of a pinball as it ricochets wildly through an immense, invisible machine. By the time one of these ultra-high-energy particles slams into the top of Earth's atmosphere, creating a massive shower of secondary particles that we can detect on the ground, its original direction has been completely scrambled. It's as if you were trying to find the source of a downpour by looking at a single, distorted raindrop that had been blown sideways for miles by a chaotic wind. This makes pinpointing their birthplace one of the most difficult tasks in all of astronomy. We know they are coming from somewhere outside our galaxy, as the Milky Way's own magnetic fields are too weak to contain particles of such extreme energy. But the where remains a tantalizing mystery. This has led scientists on a hunt for the most powerful and violent engines in the universe, places where the physics is so extreme it could, in theory, accelerate particles to these staggering velocities. One of the prime suspects are active galactic nuclei, the supermassive black holes at the hearts of distant galaxies that are actively feeding on surrounding matter. As vast quantities of gas and dust spiral into the black hole's gravitational grip, they heat up to incredible temperatures, forming a swirling, luminous accretion disk. Intense magnetic fields and powerful jets of plasma can be launched from the poles of this system, stretching for thousands of light years. It is within these relativistic jets that particles could potentially be accelerated across vast distances, gaining a little bit of energy with each magnetic bounce, much like a surfer being pushed forward by successive waves until they are riding a colossal cosmic tsunami. Another potential culprit is the gamma-ray burst, the most energetic explosive event since the Big Bang itself. These brief, blinding flashes of gamma rays are thought to be the birth cries of black holes or the collisions of ultra-dense neutron stars. The relativistic shock waves produced in these cataclysms could, in theory, serve as a perfect natural particle accelerator, injecting protons and nuclei with energies that dwarf anything we can create. Yet, even these fantastically violent events are pushed to their theoretical limits to explain the very highest energy cosmic rays we observe. This has forced physicists to consider even more exotic possibilities, such as the decay of hypothetical super-heavy relic particles from the Big Bang, or defects in the very fabric of spacetime, like cosmic strings. The search for the source is a wide-open field, with no single candidate yet proven guilty beyond a reasonable doubt. To crack this case, scientists have built enormous observatories that treat the entire Earth's atmosphere as a giant particle detector. The most prominent of these is the Pierre Auger Observatory, a colossal instrument spread over 3,000 square kilometers of the Argentine pampas. It doesn't try to catch the primary cosmic ray itself, which is impossible, but instead meticulously records the extensive air shower of billions of secondary particles that rain down when the primary particle collides with an atom in the upper atmosphere. By using a grid of over 1,600 water tanks to detect these secondary particles, and telescopes to observe the faint ultraviolet fluorescence light the shower produces, the observatory can reconstruct the energy, direction, and type of the original cosmic ray with remarkable precision. The data from Auger and other facilities has provided crucial clues. We have learned, for instance, that the very highest energy cosmic rays are not deflected as much by magnetic fields, which should, in principle, make them easier to trace. Recent observations have even hinted at a possible correlation with galaxies with active nuclei in our nearby cosmic neighborhood, a tantalizing but not yet conclusive link. The detective work continues, with plans for even larger and more sensitive observatories to gather more of these rare, high-energy messengers. Every time one of these ghostly particles from the distant cosmos strikes our atmosphere, it carries a faint imprint of its origin, a coded message about the most powerful and mysterious engines in the universe. Deciphering that message remains one of the great ongoing quests in modern astrophysics, a hunt for the ultimate cosmic accelerators. Just when you thought the cosmos couldn't get any stranger, it throws another curveball, a flash of radio energy so powerful it outshines entire galaxies, yet it lasts for less time than it takes to blink. These are fast radio bursts, or FRB, one of the most bewildering and fastest moving mysteries in modern astronomy. Imagine tuning an old-fashioned radio across the heavens and suddenly hearing a single, deafeningly loud pop, a burst of radio waves that packs more energy than the sun emits in 80 years, all compressed into a few thousandths of a second. They erupt from the deepest reaches of intergalactic space, travel for millions or even billions of years, and then vanish without a trace as quickly as they appeared. For years after the first one was discovered in 2007, these events were tantalizing phantoms. Were they cosmic one-hit wonders, the final, catastrophic death cries of unknown objects? Or were they something else entirely, something that could repeat? The answer came in 2016, when astronomers confirmed that at least one source, known as FRB 12112, was repeating. This single discovery shattered the notion that all FRBs were destructive events and opened up a vast new landscape of possibilities, launching a frantic global hunt to understand the engines behind these brilliant, fleeting flashes. The frantic search for the sources of these bursts has led astronomers to some of the most extreme objects known to physics. The current prime suspect in the cosmic lineup is the magnetar, a type of neutron star with a magnetic field so immensely powerful it defies human comprehension. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's, a force so intense that it could literally tear the electrons from your atoms from hundreds of thousands of miles away. Picture one of these city-sized, ultra-dense stellar corpses, the collapsed core of a once massive star, spinning rapidly and wound up with unimaginable magnetic stress. Theorists propose that these magnets can experience starquakes' violent ruptures on their solid, crystalline crust that release pent-up magnetic energy in a cataclysmic snap. Alternatively, the magnetic field could become so twisted and complex that it suddenly and explosively reconnects, like a cosmic short circuit, converting colossal amounts of magnetic energy into a blistering flash of radio waves that then shoots out across the universe. In 2020, a magnetar within our own Milky Way galaxy was caught in the act, producing an FRB-like burst, though significantly weaker than the extragalactic ones we detect. This was a monumental clue, strongly suggesting that magnetars are indeed one source of these phenomena. However, a major puzzle remains. Can these relatively local magnetars produce the truly titanic energies we see coming from other galaxies? Or is something even more violent required to explain the most powerful FRBs? This question has led scientists to explore other potential cosmic powerhouses. When two incredibly dense objects, like neutron stars or black holes, spiral together and finally merge, The collision releases a staggering amount of energy in gravitational waves and electromagnetic radiation. It is thought that in the chaotic aftermath of such a merger, as material is violently ejected and magnetic fields are amplified to ludicrous strengths, a single, brilliant FRB could be the final signature. This model elegantly explains the non-repeating FRBs. They are the final, fatal firework of a catastrophic union. Another compelling theory involves the exotic behavior of isolated black holes. As a black hole feeds, it can accumulate a vast, swirling disk of superheated gas and dust. Intense magnetic fields within this accretion disk could, under the right conditions, produce coherent beams of radio emission, much like a celestial lighthouse, which we would see as a repeating burst each time the beam sweeps past Earth. Some of the most recent and perplexing observations add even more layers to the mystery. Astronomers have detected FRBs that are surrounded by persistent, lower energy radio sources, suggesting they originate from incredibly turbulent and energetic environments, perhaps within young supernova remnants or dense star-forming regions. The sheer variety of FRB behaviors, some repeating with clock-like regularity, others erupting in chaotic storms of bursts, and many appearing just once, strongly implies that we are not dealing with a single cause. There may be multiple roads in the universe to creating these brilliant millisecond flashes. Given the profound and structured nature of some FRB signals, a more speculative question inevitably arises. Could some of them be artificial in origin? This is not the preferred explanation within the scientific community, but it is a possibility that must be considered, especially when nature seems to be pushing the limits of known physics. The idea was given a significant boost by the discovery of one particular repeating FRB that seemed to exhibit a strange, periodic pattern in its activity cycle, flaring up for about 90 days and then going silent for 67 days. While such long-term cycles can often be explained by orbital motion in a binary star system, the precision is striking. If an advanced civilization wanted to announce its presence across the cosmos, a tightly beamed, incredibly powerful radio burst would be an efficient way to do it. The energies required, while astronomical to us, might be trivial for a Type II civilization on the Kardashev scale, one capable of harnessing the total energy output of its star. They could use such bursts for interstellar communication, or perhaps for powering massive light sails on interstellar spacecraft, where a focused beam of energy pushes a vessel to relativistic speeds. The main argument against this technological hypothesis is one of sheer energy. The most powerful FRBs release as much energy in a millisecond as our sun does in decades. The engineering required to generate that kind of power is, to our minds, godlike. Furthermore, the signals we detect have traveled across millions of light years, meaning that if they were indeed a message, it was sent when life on Earth was in its most primitive state, long before any intelligence arose. The consensus remains that a natural explanation is far more likely, but the very fact that the question can be seriously entertained highlights just how extraordinary and unexplained these cosmic signals truly are. The field is moving at a breathtaking pace, with new telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, discovering hundreds of new FRBs, each one adding a new piece to the puzzle. We are witnessing, in real time, the birth of a new branch of astronomy, one that is revealing a universe far more dynamic and explosive than we ever imagined, all playing out in the blink of an eye. But our journey doesn't stop at the edge of our own galaxy. We are part of a much larger cosmic migration, a vast and silent river of galaxies all flowing in the same direction. For decades, astronomers have known that our Milky Way is not sitting still. It is moving at an incredible speed of over 2 million kilometers per hour. But relative to what? This motion is not just the general expansion of the universe, which pushes all galaxies apart. This is a specific, targeted drift. We, along with our entire local group of galaxies, including the Great Andromeda, are being pulled. The source of this immense gravitational tug is a mysterious, hidden region of space known as the Great Attractor. Picture a colossal, unseen weight in the cosmic fabric, a gravitational sinkhole so powerful that it is drawing our Milky Way and thousands of other galaxies toward a point in space roughly 250 million light-years away, in the direction of the southern constellations Centaurus and Norma. The sheer scale of this influence is staggering, dominating the motion of galaxies across a region hundreds of millions of light-years wide. The intrigue of the Great Attractor is magnified by a frustrating cosmic coincidence. It lies directly behind the plane of our own Milky Way galaxy, in a region astronomers call the zone of avoidance. Think of our galaxy as a vast, spiraling disk of stars, gas, and dust. When we look out into the universe along the plane of this disk, our view is completely obscured. It's like trying to see a distant city while standing in the middle of a dense, foggy forest. The light from distant galaxies and clusters is blocked, absorbed, or scattered by all the cosmic material in our own backyard. For a long time, this meant the heart of the Great Attractor was hidden from our optical telescopes, shrouded in a veil of interstellar dust. We could feel its immense gravitational pull, measuring the peculiar velocities of the galaxies being drawn toward it, but we couldn't see what was causing it. This created a classic scientific detective story. We had the evidence of a crime, the motion of the galactic suspects, but the prime culprit was hiding in a dark alley we couldn't peer into. Determined to lift this cosmic veil, astronomers turned to instruments that could see through the dust. Just as certain types of radiation can pass through your skin to reveal the bones beneath, different wavelengths of light can penetrate the dusty plane of the Milky Way. Radio telescopes, infrared observatories, and most notably, X-ray telescopes like the Rosat satellite, began to map the hidden landscape. They slowly peeled back the layers of obscuration, revealing that the Great Attractor was not a single, monstrously dense object, but rather the central gravitational core of a vast supercluster of galaxies. The initial pull we were feeling was the combined gravity of this enormous concentration of mass. But the story didn't end there. As our maps of the large-scale structure of the universe improved, an even grander picture emerged. The Great Attractor itself was not the final destination, but merely a waypoint in a much larger cosmic journey. Our local supercluster, including the Great Attractor, our own Milky Way, and tens of thousands of other galaxies, is all part of an incomprehensibly vast structure now known as the Laniakea supercluster. Laniakea is a Hawaiian word meaning immense heaven, and the name is perfectly fitting. This cosmic continent spans over 500 million light-years and contains the mass of about 100 quadrillion suns. Within Laniakea, all galaxies are streaming along a complex web of filaments toward a common center of gravity, a region known as the Great Attractor Basin. So, the Great Attractor is the gravitational heart of our local supercluster, the central point toward which everything in our immediate cosmic neighborhood is slowly, inevitably falling. This revelation shifts the mystery rather than solving it completely. What defines the center of Laniakea and creates such a powerful gravitational focus? The leading theory points to an even greater concentration of mass known as the Norma cluster. a dense knot of galaxies located very near the heart of the Great Attractor region. This cluster, along with surrounding filaments of dark matter and galaxies, creates the deep gravitational well that orchestrates the motion of our entire supercluster. Yet, the pull doesn't stop with Laniakea. There are hints of structures beyond, with names like the Shapley Attractor, that may be pulling on Laniakea itself. We find ourselves in a cosmic hierarchy of pulls within pulls, a cascade of gravitational influence that stretches across the observable universe. The Great Attractor, once a singular enigma, is now understood as a key landmark in this grand map, a testament to the relentless pull of gravity on the very largest scales, shaping the paths of galaxies over billions of years. From the immense flows of galaxies toward the Great Attractor, we can step back even further to see the grandest architecture of all, the universe's large-scale structure, which reveals itself not as a random scattering of galaxies, but as a magnificent, intricate cosmic web. When we map the positions of millions of galaxies across vast volumes of space, a breathtaking pattern emerges, one of immense filaments and walls of galaxies stretching for hundreds of millions of light years, surrounding equally immense, nearly empty voids. This structure is often described as resembling a sponge or a network of interconnected neurons on a cosmic scale. It is the dominant organizational pattern of the visible universe, and its origin story is written in the faintest whisper of a signal from the dawn of time. The seeds for this entire colossal arrangement were planted in the first fleeting moments after the Big Bang, during a period of hyper-expansion known as cosmic inflation. According to this theory, the microscopic quantum world and the macroscopic cosmic world became inextricably linked. The vacuum of space, far from being truly empty, is a seething foam of virtual particles constantly flickering in and out of existence. Inflation stretched these quantum fluctuations in the energy field to astronomical sizes, imprinting them onto the fabric of the cosmos. These tiny ripples in density, these faint over and under densities, were the blueprints for everything to come. They were the cosmic eggs from which galaxies, clusters, and the great filaments would eventually hatch. After inflation ended, the universe was a hot, dense plasma, and these imprinted density variations played a crucial role. Gravity, the great sculptor, began its work over billions of years. Regions that were slightly denser than average had a stronger gravitational pull, slowly drawing in more and more matter from their surroundings. Meanwhile, the less dense regions were left behind, emptying out over cosmic time. Picture a landscape of gentle hills and shallow valleys being carved by rainfall. The water naturally flows from the high points into the valleys, deepening the channels and raising the peaks. In the cosmos, dark matter acted as the invisible skeleton for this process. Because it does not interact with light, it could begin clumping together long before normal matter, forming gravitational wells into which ordinary atoms would later flow. This gravitational tug-of-war, acting on the initial blueprint of inflation, is what woven the cosmic web. The densest knots grew into the massive galaxy clusters we see today. The elongated tendrils of matter became the great filaments, connecting clusters like cosmic highways. And the vast regions that started with the slightest deficit of material evolved into the enormous voids, cosmic deserts that can span hundreds of millions of light years and contain almost no galaxies at all. This leads to a profound and tantalizing question. As we map this web in ever greater detail, are we seeing a truly random, if structured, distribution, or is there a deeper, hidden pattern, a fractal or geometric order, that we haven't yet deciphered? A fractal is a pattern that repeats itself at different scales. Think of a fern frond, where a small part of the leaf looks similar to the whole leaf. Some scientists have wondered if the universe exhibits this property. Does a small cluster of galaxies, when magnified, reveal a structure that resembles the entire cosmic web? The current evidence suggests that the universe is not a perfect fractal. On the very largest scales, beyond about 300 million light-years, the distribution of matter appears to smooth out and become homogeneous, meaning it looks roughly the same in every direction. This is a key assumption in modern cosmology. However, within that scale, the pattern of clusters, filaments, and voids does show a striking self-similarity, a complex hierarchy of structure that is neither purely random nor perfectly orderly. It exists in a fascinating middle ground, a complex system that emerged from simple initial conditions governed by the laws of gravity and physics. Discovering a deeper pattern, if one exists, would be revolutionary. It could point toward new fundamental laws or constraints that govern the inflationary epoch, laws we currently know nothing about. For instance, some speculative theories in quantum gravity suggest that the fabric of spacetime itself may have a discrete, pixelated structure at the tiniest possible scale, the Planck length. If this is true, then the large-scale structure of the universe might bear the imprint of this underlying granularity, much like a digital image reveals its pixelated nature when you zoom in close enough. Finding a specific geometric pattern in the cosmic web could be the first observational evidence for such a theory. Alternatively, a hidden pattern could reveal something about the nature of the dark matter particle itself. Different types of dark matter, such as cold dark matter versus slightly warm dark matter, would produce subtly different web structures. Cold dark matter, which moves slowly, allows for a very fine-grained web with many small clumps and filaments. Warm dark matter, consisting of faster-moving particles, would suppress the formation of structure on small scales, resulting in a web that is coarser and more streamlined. By meticulously comparing the observed cosmic web to supercomputer simulations that model different dark matter properties, we are essentially running a cosmic fingerprint analysis, trying to match the pattern we see to the identity of the invisible particle that shaped it. The quest to map and understand this cosmic architecture is one of the primary drivers of modern astronomy. Projects like the Sloan Digital Sky Survey have painstakingly charted the positions of millions of galaxies, revealing the web in stunning detail. Future observatories like the Vera C, Rubin Observatory, and the Euclid Space Telescope are set to extend these maps to billions of galaxies, probing the cosmic web across vast stretches of space and time. By observing how the web has evolved over billions of years, we can trace the history of cosmic structure formation and put our theories of gravity, dark matter, and dark energy to their most rigorous test. The large-scale structure is more than just a beautiful pattern in the sky. It is a rich historical archive, a frozen record of the forces that have shaped the universe from its quantum origins to the present day. Decoding its deepest patterns is akin to learning a new language, the native language of the cosmos itself, one that tells the story of how everything we see came to be. We have explored the cosmic web and the great flows of galaxies, but to understand the universe at its most fundamental level, we must confront a dimension that is woven into our every moment, yet remains deeply mysterious, the very nature of time itself. We all know how to measure it with clocks and calendars, but what is it? Is it a river that flows uniformly for everyone? Or is it something far more strange and malleable? Our most intuitive experience of time is that it has a direction, a clear arrow pointing from the past, through the present, and into the future. You can remember yesterday, but you cannot remember tomorrow. A cracked egg spontaneously splatters into a messy puddle on the floor. It never spontaneously reassembles itself into a pristine, whole egg. This one-way street of cause and effect is what physicists call the arrow of time, and its origin is one of the most profound puzzles in science. The most widely accepted explanation for this arrow comes from the second law of thermodynamics, which states that in an isolated system, a property called entropy, a measure of disorder or randomness, always increases over time. The universe as a whole started in a state of incredibly low entropy just after the Big Bang, an extremely ordered and uniform state of immense energy density. Ever since, it has been evolving toward a state of higher entropy, becoming more disordered and spread out. The reason we remember the past and not the future is that the past was in a state of lower entropy. Our memories are formed by irreversible processes, light hitting your retina, neural connections being forged, that increase the overall disorder in the universe. The arrow of time is therefore tied to the universe's journey from order to disorder, from a unique beginning toward an eventual state of maximum randomness. Yet, this explanation immediately leads to a deeper question. Why was the entropy of the early universe so low to begin with? The laws of physics, as we currently understand them, are almost entirely time-symmetric. The equations that describe how particles interact work just as well running forward as they do backward. There is no fundamental law that commands entropy must increase. It simply does so as a matter of overwhelming probability. If you shuffle a new deck of ordered cards, it will almost certainly become disordered. It's not impossible for a random shuffle to return the deck to its original order, but it is astronomically unlikely. So the real mystery of the arrow of time is not in the laws themselves, but in the initial condition of the cosmos. Why did our universe begin in such a spectacularly unlikely state of low entropy? Some physicists, like Sean Carroll, suggest that the low entropy Big Bang might not have been the absolute beginning, but could instead be explained by a larger multiverse context, where our universe is just one region in a vast cosmic landscape. The arrow of time, then, may not be a fundamental property of reality, but rather a feature of our particular cosmic neighborhood, a contingent fact of our history. This classical view of time's flow was completely upended by a young patent clerk named Albert Einstein. His theories of special and general relativity shattered the Newtonian idea of a universal, ticking clock. Einstein revealed that time is not absolute, it is relative. The rate at which time passes depends entirely on your speed and the strength of the gravitational field you are in. This is not a theoretical abstraction. It is a measurable effect that is crucial for the GPS in your phone to function correctly. Satellites in orbit, moving at high speed and in a weaker gravitational field than Earth's surface, experience time flowing slightly faster. If these tiny differences were not corrected for, your GPS would be inaccurate by several miles within a single day. Einstein's great insight was to fuse the 3 dimensions of space with the 1 dimension of time into a single 4-dimensional continuum called spacetime. In this block universe model, past, present, and future all exist simultaneously, laid out in a static, unchanging structure. From this God's eye view, the entire history of the universe, from the Big Bang to this very moment, to the heat death of the cosmos, is just a fixed landscape. Your life is not a movie that is being projected. It is the entire film reel, complete and entire. The feeling of now and the flow of time in this picture are not fundamental features of the world, but rather a perspective that emerges from within the block, a kind of cognitive illusion. This brings us to the most radical and contentious frontier of the debate. Is time real, or is it an emergent property, an illusion created by the limitations of our consciousness? Many physicists working on quantum gravity, the sought-after theory that would unite general relativity with quantum mechanics, find that their equations work more elegantly when time is removed from the picture entirely. In some approaches, like the Wheeler-DeWitt equation, time simply does not appear. The universe is described by a timeless wave function. If time is not fundamental to the universe's most basic laws, then what is the now that we feel so vividly? Some philosophers and cognitive scientists propose that the flow of time is a construct of our brains, a necessary narrative we create to make sense of the world. Our consciousness, they argue, takes a series of static snapshots from the block universe and strings them together, creating the compelling but ultimately false sensation of a flowing present. We are like a needle reading the grooves on a vinyl record. The entire song is physically present on the disc, but we experience it moment by moment. The deep tension between the timeless, four-dimensional spacetime of relativity and the undeniable, flowing now of human experience represents one of the greatest gulfs between the scientific description of reality and our lived reality. The nature of time sits at the crossroads of physics, philosophy, and neuroscience, a mystery that challenges not only our understanding of the cosmos, but the very nature of our own conscious existence. After charting the grand architecture of the cosmos and the strange nature of time, our journey brings us to perhaps the most personal and profound mystery of all. How did life begin, and is this spark of biology a common feature of the universe, or a singular, miraculous accident? We are made of star stuff, atoms forged in the hearts of long-dead stars, yet the leap from inert chemicals to a living, reproducing cell is a chasm we have yet to cross in our understanding. On Earth, the evidence suggests life appeared with surprising swiftness. The planet itself formed around 4.5 billion years ago, and the earliest signs of microbial life date back to at least 3.8 billion years ago, a time when the Earth's surface was still a violent, bombarded hellscape. This means that within a geologically brief window of just a few 100 million years, the right chemistry somehow organized itself into something that could eat, grow, and replicate. The process by which this happened is called abiogenesis, and while we may never know the exact sequence of events, scientists have proposed several compelling scenarios for where this genesis could have occurred. One of the leading theories points to the deep, dark ocean floor, to hydrothermal vents known as black smokers. These are not gentle hot springs, but towering chimneys spewing superheated, mineral-rich water into the frigid depths. What makes them such a compelling cradle for life is that they provide both energy and a stunningly complex gradient of chemicals. The porous rock of the vent structures acts like a natural laboratory, creating millions of microscopic chambers that could have concentrated simple organic molecules, allowing them to interact and form more complex chains like amino acids and lipids. Crucially, these vents also offer a potential solution to a key puzzle: the origin of metabolism. The sharp difference in chemistry between the vent fluid and the surrounding ocean creates a natural proton gradient, a flow of energy that is eerily similar to the process modern cells use to power themselves. It's as if the early Earth provided a ready-made power source, and the first life forms simply learned to plug into it. Another prominent hypothesis suggests a very different nursery, shallow pools on land, cycling through wet and dry phases. Imagine a tidal pool or a volcanic hot spring under the young sun. As the water evaporates and refills, it could concentrate the building blocks of life, while the sun's ultraviolet radiation and lightning strikes provided the energy to forge them into more complex molecules like nucleotides, the building blocks of RNA. This primordial soup model, while classic, faces challenges, particularly in explaining how these fragile molecules were protected and concentrated enough to take the next critical step. That next step is perhaps the most difficult one to explain: the emergence of a system that can both store information and catalyze its own replication. Many scientists now believe the first truly living entity was not a DNA-based cell, but an RNA world. RNA is a remarkable molecule. It can store genetic information like DNA, but it can also act as an enzyme, catalyzing chemical reactions, including the copying of itself. In this view, the first spark of life might have been a self-replicating RNA molecule that emerged from the chemical chaos, enclosed by a simple fatty membrane. Once this system could make copies of itself, however imperfectly, natural selection kicked in, and the relentless engine of evolution began to turn. There is, however, a more cosmic alternative to these terrestrial origins: the idea of panspermia. This theory suggests that the raw ingredients for life, or perhaps even simple life forms themselves, are common throughout space and were delivered to Earth by comets, asteroids, or interstellar dust. We know that amino acids, the building blocks of proteins, have been found on meteorites, and comets are rich in organic molecules. It's possible that the early solar system was a vast shooting gallery, swapping material between planets, and that life, or its precursors, hitched a ride from Mars to Earth on a blasted piece of rock. While this elegantly sidesteps the problem of abiogenesis on Earth, it simply pushes the ultimate question of life's origin elsewhere, to another world, or even to the swirling clouds of interstellar space. This brings us to the second part of the question, with implications that shake our view of our place in the cosmos. Is the transition from chemistry to biology an easy, almost inevitable process on any suitable world? Or was Earth the winner of an inconceivably rare cosmic lottery? The optimistic view rests on the principles of probability and chemistry. The universe is immense, with an estimated 100 billion galaxies, each containing hundreds of billions of stars. A significant fraction of those stars are now known to host planets, and many of those planets will orbit within the habitable zone, where temperatures allow for liquid water. The building blocks of life, carbon, hydrogen, oxygen, nitrogen, are among the most common elements in the cosmos, and we find complex organic molecules everywhere we look, from the atmospheres of gas giants to the depths of interstellar nebulae. Given the right conditions and enough time, the laws of chemistry and physics might naturally favor the self-organization of matter into living systems. In this view, life is not a miracle, but a natural property of matter, an emergent phenomenon that arises as predictably as crystals forming from a saturated solution. If this is true, then the galaxy should be a verdant oasis, filled with planets where life has taken root. The opposing, more sobering perspective is that while the ingredients are common, the recipe is impossibly complex. The journey from a pool of organic soup to a self-replicating cell involves a series of steps, each one staggeringly improbable. How did simple molecules first form complex polymers? How did a genetic code emerge to translate information into function? How did the first cell membrane form to separate the living system from its environment? It is possible that each of these transitions represents a monumental barrier, a bottleneck that few, if any, planets ever manage to pass. The fact that life appeared on Earth so quickly could be a powerful illusion. It might not mean the process is easy, but rather that we are the beneficiaries of an incredibly fortuitous fluke, a 1 in a trillion occurrence that happened to play out here. If this is the case, then the great filter we discussed earlier, the barrier that prevents life from becoming widespread, may lie in the very act of abiogenesis itself. We might be alone, not because civilizations destroy themselves, but because life almost never gets started in the first place. The silent, empty cosmos would then not be a mystery, but the expected state of a universe where the spark of life is a fleeting, precious, and exceptionally rare event. The answer to this question will not be found in our telescopes alone, but in our laboratories, as we strive to recreate that moment of genesis and understand whether life on Earth is a cosmic prototype or a solitary masterpiece. And so we return to the shadowy realm of black holes, not to gaze upon their event horizons, but to confront a paradox so fundamental it threatens to unravel our understanding of reality itself. This is the black hole information paradox, a puzzle that pits the two pillars of modern physics, Einstein's general relativity and quantum mechanics, against each other in a battle with seemingly no compromise. To grasp the depth of this conflict, we must first understand a discovery that shook the world of theoretical physics to its core. For decades, black holes were thought to be the universe's ultimate dead ends, cosmic prisons from which nothing, not even a single bit of information, could ever escape. Then, in the 1970s, Stephen Hawking made a startling theoretical leap. He realized that by applying quantum theory to the curved space just outside a black hole's event horizon, a remarkable process should occur. The intense gravitational field can spontaneously create pairs of virtual particles from the vacuum of space. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But right at the edge of the event horizon, a cosmic robbery can take place. One particle of the pair falls into the black hole, while its partner escapes into space, carrying energy with it. To an outside observer, this stream of escaping particles is known as Hawking radiation. The implications of this are staggering. Because the radiation is carrying energy away, the black hole is slowly losing mass. Over inconceivably vast stretches of time, a black hole will evaporate, shrinking until it potentially vanishes completely. This presents a beautiful connection between gravity, quantum theory, and thermodynamics. But it also creates a catastrophic problem. Hawking's calculations showed that this radiation is entirely random and thermal. It is a featureless hiss of heat, like the glow from a hot piece of coal. It contains no information whatsoever about the intricate details of the objects that formed the black hole or later fell into it. Whether you throw a perfect diamond, a library of encyclopedias, or a box of confetti into a black hole, according to Hawking's original work, the resulting Hawking radiation would be exactly the same. When the black hole finally evaporates, all the specific, detailed information about those objects would be permanently erased from the universe. This violates one of the most sacred principles of quantum mechanics, the law of unitarity, which demands that information is never truly lost. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. The information paradox is this stark choice. Either Hawking was wrong and information can escape, which breaks our understanding of black holes, or quantum mechanics is wrong, which would force us to rewrite the rules governing the entire subatomic world. The scientific community has been grappling with this for half a century, and the debate has produced several leading and deeply strange potential solutions. One of the most profound ideas is that information never actually makes it to the singularity. Instead, it is stored in a scrambled, two-dimensional form on the event horizon itself. This is the essence of the holographic principle. Think of the event horizon not as a destructive boundary, but as a vast, cosmic hard drive. Every bit of information about an object falling in the precise arrangement of its atoms, its color, its shape, is encoded onto the surface area of the horizon, pixelated in unimaginably tiny Planck-scale units. The three-dimensional interior of the black hole, in this view, is a projection of this two-dimensional information. Much like a hologram appears three-dimensional, but all its information is stored on a flat surface. When Hawking radiation is emitted, it's not random. It gradually reads out this encoded information, slowly and carefully peeling the data off the horizon. The radiation only appears random and thermal when you look at small parts of it. But if you could collect all the radiation over the black hole's entire multi-trillion-year lifetime, you would find the complete story of everything that ever fell in, perfectly preserved. This solution elegantly saves quantum mechanics, but it forces us to accept a radically new view of reality, that the three-dimensional world we experience might itself be a holographic projection of information stored on a distant, two-dimensional surface. A more drastic and violent proposal is the black hole firewall hypothesis. Imagine an astronaut right at the moment of crossing the event horizon. According to classical general relativity, this should be a smooth, uneventful process. The astronaut should feel nothing special, a concept known as the no-drama principle. But the firewall idea suggests this peaceful picture is an illusion created by our incomplete theories. To resolve the information paradox and prevent information from being lost, a searing wall of ultra-high-energy particles might exist just inside the event horizon. This firewall would instantly incinerate anything falling in, vaporizing it, and imprinting all of its information directly onto the outgoing Hawking radiation. In this scenario, information is saved, but at a terrible cost. It completely shatters Einstein's principle that free fall should be smooth and local physics should be predictable. The event horizon becomes a place of immense, destructive energy, a dramatic boundary where the laws of physics, as we know them, fundamentally break down. The firewall forces a brutal either-or choice. Either information is preserved and the interior of a black hole is a raging inferno, or the interior is peaceful and information is lost forever. More recent work has begun to bridge these extreme views, suggesting a more subtle and complex resolution. One compelling line of thinking involves the quantum entanglement of particles. The Hawking radiation particles are entangled with their partners that fell into the black hole. As the black hole evaporates, this web of entanglement becomes increasingly complex and strained. To preserve the consistency of quantum mechanics, these entanglements must somehow be transferred to the outgoing radiation itself in a precise way. This process could create a highly chaotic but non-violent region just inside the event horizon, not a literal firewall of energy, but a computational firewall of immense complexity, where information is furiously processed and encoded in the radiation. Another fascinating idea is that black holes don't evaporate completely. Instead, they leave behind a tiny, stable remnant, a fossil containing all the information that ever fell into the original black hole, locked within an object smaller than an atom yet containing the information of entire stars. The problem with this is that such a remnant would have to be able to store an almost infinite amount of information in a finite space, pushing the limits of what we believe is physically possible. The search for a definitive answer continues, driving the development of new theories of quantum gravity. The information paradox is not just an abstract puzzle. It is a powerful beacon, guiding us toward a deeper theory of everything, forcing us to peer into the heart of a black hole and decide what fundamental principles our universe ultimately holds most sacred. We take the rules of the universe for granted. The speed of light in a vacuum is always 299,792,458 meters per second. The force of gravity weakens with the square of the distance, a relationship that holds true from the orbit of Mercury to the dance of galaxies billions of light years away. This principle, the assumption that the fundamental laws and constants of physics are the same everywhere in the universe and have been for all time, is the bedrock of modern cosmology. It's called the principle of uniformity. It's what allows us to look at the light from a galaxy 10 billion light years away and be confident that the atomic physics governing the emission of that light is identical to the physics we study in our laboratories on Earth. Without this foundational belief, the entire scientific enterprise of cosmology would crumble. We could never use observations of the distant cosmos to understand its history, because we'd have no guarantee that the rules of the game weren't different back then. But what if this cornerstone of our understanding is wrong? What if the laws of physics themselves are not eternal and universal, but are merely local bylaws, capable of changing over cosmic time or varying from one region of space to another? This seemingly philosophical question has been thrust into the realm of hard, observational science thanks to a decades-long investigation of one of the most esoteric numbers in physics, the fine structure constant. Often denoted by the Greek letter alpha, this constant is a pure, dimensionless number that governs the strength of the electromagnetic force. It controls how tightly electrons are bound to atomic nuclei, the specific wavelengths of light that atoms absorb and emit, and the very nuclear reactions that power stars. Its value, approximately 1/137, is so precisely tuned that even a small change would make our universe unrecognizable. For a long time, it was simply accepted as a fixed feature of reality. But then, around the turn of the millennium, a team of astronomers led by John Webb began to look at this constant in a new way by observing the ancient light from quasars, the incredibly bright cores of distant galaxies. Their method was both simple and brilliant. As light from a quasar travels billions of light years to reach us, it passes through clouds of interstellar gas. Atoms in these clouds, like iron, magnesium, and silicon, absorb specific wavelengths of this light, leaving behind a unique fingerprint of dark lines in the quasar spectrum. The precise positions of these absorption lines are determined by the value of the fine structure constant in those distant clouds. By comparing these ancient fingerprints to the patterns we see in laboratories on Earth today, Webb's team could effectively measure the value of alpha as it was billions of years ago, in a different part of the cosmos. The results sent shockwaves through the physics community. Their data, painstakingly collected over years using the world's most powerful telescopes, suggested that the fine structure constant was ever so slightly smaller in the distant past. The change was minuscule, a few parts in a million, but if true, the implications were earth-shattering. It would mean that the electromagnetic force was marginally weaker billions of years ago, that the very rules of atomic physics were not fixed, but in a state of slow, cosmic evolution. The scientific response was as expected. one of intense scrutiny and skepticism. Such a monumental claim requires extraordinary evidence. Other teams have attempted to replicate the findings, with some supporting the initial results and others finding no variation at all. The debate is far from settled, and the measurements sit at the very edge of our technological capabilities, vulnerable to subtle systematic errors. Yet, the possibility itself is what is so profoundly unsettling. If the fine structure constant can change, then perhaps other constants can too. Maybe the strength of gravity, or the mass of an electron, or even the speed of light itself, were different in the early universe. This idea, known as the theory of varying constants, is not just a minor adjustment to our models. It would represent a paradigm shift on a scale not seen since the Copernican revolution. We would have to abandon the idea of a single, universal set of laws and embrace a cosmos where the rulebook is written in fading ink, or where different volumes of space operate under different sets of fundamental parameters. What could cause such a drift in the laws of nature? One compelling, albeit speculative, explanation comes from string theory, a leading candidate for a theory of quantum gravity. In string theory, the fundamental constants we observe are not truly fundamental. They are the result of how additional, hidden dimensions of space are curled up and compactified. The specific shape of this hidden landscape, known as a Calabi-Yau manifold, determines the values of constants like alpha. In this view, our universe is just one point in a vast landscape of possible universes, each with different physical laws. The idea of varying constants suggests that this landscape is not entirely static. Perhaps our region of the cosmos is slowly evolving, its hidden dimensions shifting shape over billions of years, causing a gradual drift in the laws of physics as we experience them. We would be living in a cosmic province with its own local customs, and those customs are slowly changing with time. The implications ripple out into every corner of physics and philosophy. For cosmology, it could solve some long-standing puzzles. The observed amount of dark energy, for instance, is famously many orders of magnitude smaller than what quantum field theory predicts. If the constants were different in the early universe, it might explain why our cosmos ended up with this peculiarly small value, allowing galaxies and life to form. For the search for extraterrestrial life, it adds another layer of complexity. Could life only arise in cosmic epochs, or in specific galactic neighborhoods where the constants fall within a narrow, habitable window? We might not just be in a Goldilocks zone around a star, but in a Goldilocks era in cosmic history. And on a deeply human level, it challenges our place in the cosmos once again. Copernicus moved us from the center of the universe. Hubble showed us we are in an expanding cosmos among countless galaxies. And now we are faced with the possibility that the very fabric of reality, the laws we use to define our existence, may be transient and provincial. The quest to determine if our physics is truly universal is more than a technical exercise. It is a fundamental inquiry into the nature of reality itself, a search to see if the cosmos is governed by a single, eternal symphony, or if we are simply hearing the local melody of our own small corner of an ever-changing multiverse. We have mapped the universe's grand architecture and probed the constancy of its laws. But one of the most perplexing clues to its true nature comes from the oldest light we can see, the cosmic microwave background, or CMB. This is the remnant glow from the Big Bang itself, a snapshot of the universe when it was just 380,000 years old, cooling from a dense plasma into a transparent gas. This faint, all-sky radiation is the cornerstone of modern cosmology. and its tiny temperature fluctuations, just millionths of a degree, provided the blueprint for all the galaxies and clusters we see today. For decades, our most fundamental assumption has been that the universe is isotropic and homogeneous, that on the largest scales, it looks the same in every direction and has no preferred center or axis. The CMB data has largely confirmed this, showing a beautiful, random pattern of hot and cold spots that fit our models almost perfectly. But buried within that near perfection is a set of bizarre, large-scale anomalies that refuse to fit the standard story. And the most famous and troubling of these is what scientists have dramatically nicknamed the axis of evil. This mysterious axis isn't a physical structure or some cosmic battlefront. It's an unexpected alignment in the very fabric of the CMB. When scientists analyze the largest patterns in this ancient light, they find that the fluctuations seem to be correlated or aligned along a particular preferred direction in space. It's as if the entire early universe was subtly tilted on a specific axis. One of the most striking manifestations of this is in the behavior of the multipoles. Without getting too technical, imagine breaking down the CMB map into different components. Much like a musical chord can be broken down into its fundamental note and its higher harmonics. The lowest, most fundamental notes of the CMB, the dipole and quadrupole should, according to our standard theories, be completely random and independent of one another. Yet, when we look at the data, their orientations appear strangely aligned with each other, and even with the plane of our own solar system. This is deeply unsettling. It suggests that the largest scale structures in the primordial universe might be linked to our own local cosmic neighborhood, a connection that should be statistically impossible if the cosmos is truly isotropic. The axis of evil is the name given to this preferred plane of alignment, a ghostly line running through the cosmos that seems to define a special direction, breaking one of our most cherished cosmological principles. So, what could this mean? Scientists have proposed several possibilities, ranging from the mundane to the revolutionary. The first and most conservative explanation is that it's simply a statistical fluke. When you have a massive dataset like the CMB, there's always a chance that some patterns will look strange just by pure random chance. We might be the cosmic equivalent of someone who finds a cloud that looks exactly like their face. It's a striking coincidence, but it doesn't mean the atmosphere is sending them a personal message. Perhaps we are just seeing a pattern that stands out to our human brains in an otherwise random field. And with more precise data, the apparent alignment will fade into the background noise. The second possibility is that it's not a feature of the universe at all, but a systematic error in our measurements. Our view of the cosmos is filtered through our own Milky Way galaxy. Foreground emissions from galactic dust and synchrotron radiation could be contaminating the CMB signal, creating an illusion of large-scale alignment. Alternatively, the way we process the raw satellite data to remove these foregrounds might inadvertently be introducing or amplifying these strange correlations. Teams have worked tirelessly to rule this out, and while some foreground effects are present, they don't seem sufficient to fully explain the strength and persistence of the axis of evil signal. If it's neither a fluke nor an error, then we are left with the truly mind-bending possibility that the axis of evil is real, and that it points toward a flaw in our standard cosmological model, or even a glimpse of physics from before the Big Bang. One extraordinary idea is that this preferred axis is a fossil imprint from the epoch of inflation, the period of hyper-expansion that occurred just after the Big Bang. Perhaps the inflationary field that drove this expansion was not perfectly uniform, but had a slight directional preference, stretching the universe more in one direction than in others, leaving a permanent, subtle warp in the fabric of spacetime that we see frozen in the SIMB. An even more radical proposal is that the axis of evil is evidence that our universe is not infinite and uniform, but has a complex, non-trivial topology. Imagine the universe is shaped like a video game world where if you travel far enough in one direction, you return from the opposite side. In such a finite universe, the CMB light could wrap around and create correlations and alignments on scales larger than our observable horizon, making it appear as if there is a special axis. The most profound and most speculative interpretation is that this alignment is a cosmic bruise evidence that our universe collided with another bubble universe in the greater multiverse during its earliest moments. Such a collision would have injected a tremendous amount of energy along a specific direction, creating a permanent anisotropy that we now detect as the axis of evil. It would be our first indirect observational clue to a reality that exists beyond our own cosmic bubble, a shadow from a larger cosmic ocean. Whatever the true explanation, the axis of evil stands as a stubborn challenge to our understanding, a cryptic message from the dawn of time that reminds us the universe may still be keeping its biggest secrets. Among the countless hisses and crackles of cosmic radio noise, one signal stands apart, a singular burst of data so extraordinary it earned the most human of reactions. A single word, wow, scrawled in red ink by an astonished astronomer. This event, which occurred on the evening of August 15, 1977, at the Big Ear Radio Telescope in Ohio, has become the stuff of scientific legend, the closest we have ever come to potentially hearing a sign from another civilization. For 72 unforgettable seconds, the telescope, which was scanning the sky as part of the ongoing search for extraterrestrial intelligence, or SETI, locked onto something unprecedented. The signal was not a random blast of static. It was a powerful, focused, narrowband radio transmission centered on the frequency of 1,420 megahertz. This specific frequency is significant because it is one of nature's quiet zones, a region of the radio spectrum where background noise from hydrogen and hydroxyl molecules is minimal. It's a channel many scientists have suggested would be a logical choice for an advanced civilization trying to get noticed across the interstellar void. The signal's intensity rose and then fell over exactly 72 seconds, perfectly matching the expected profile as the Earth's rotation swept the Big Ear's fixed field of view across a fixed point in the sky. This clear, bell-shaped curve confirmed the signal was coming from a specific celestial location, not from a passing airplane or a terrestrial source of interference. The astronomer on duty that night, Jerry Amon, was meticulously reviewing the computer printouts a few days later when he saw the alphanumeric sequence, 6 characters 6 EQUJ5. This code represented the signal's intensity, and this particular sequence was off the charts. The letter U, corresponding to an intensity 30 times greater than the background noise, was the highest value the system could record. It was at this moment that Amon, overwhelmed by the sheer improbability of what he was seeing, circled the sequence and wrote his now famous exclamation in the margin. The signal's characteristics pointed overwhelmingly to an origin far beyond Earth. It was a pure, unmodulated carrier wave, the kind of simple, powerful beacon a civilization might use to announce its presence. It appeared to come from the direction of the constellation Sagittarius, in a region of the sky devoid of any known stars or planetary systems at the time. though subsequent analysis has suggested it could have originated from a sun-like star nearly 2,000 light-years away. Crucially, the signal was observed by only one of the Big Ear's 2 adjacent beams, which was exactly what you would expect from a genuine cosmic source. If it had been a local signal from Earth, it would have flooded both beams simultaneously. Every test and recheck seemed to rule out a prosaic explanation. It wasn't a secret military transmission, a satellite, or a reflection from space debris. It behaved exactly as a signal from an interstellar source should behave. Fueled by this incredible discovery, astronomers immediately began efforts to hear it again. The Big Ear telescope spent months, and eventually years, repeatedly scanning the same patch of sky, its operators hoping for a repeat performance. Other, more sensitive radio telescopes around the world were directed toward the coordinates, listening intently for any whisper of a return, but the cosmos offered only silence. The WOW signal was a one-time event, a cosmic flash in the pan that has never been replicated. This singular nature is at the heart of its enduring mystery. If it was a deliberate broadcast from an alien civilization, why was it so brief? Why send a powerful signal for just 72 seconds and then fall silent forever? One possibility is that it was indeed a targeted message, but we were not the intended recipient. We may have simply drifted through the edge of a tightly focused communication beam meant for another star system, catching only a fleeting, unintended glimpse. Alternatively, it could have been a one-time event for the senders as well. Perhaps a powerful radar used for mapping asteroids in their own system that momentarily pointed in our direction, or even the catastrophic explosion of an interstellar vessel, releasing a final, powerful burst of energy. The lack of a repeat signal has also fueled more skeptical, natural explanations. Some scientists have proposed that the signal was caused by a comet. Decades after the event, one astronomer suggested that 2 comets, which were not known to be in that part of the sky in 1977, could have been the source, with their vast clouds of hydrogen emitting a transient radio burst. However, this hypothesis has been largely dismissed by the broader astronomical community, as comets are not known to produce such intense, narrowband signals at that specific frequency. Another idea is that the signal was the result of a gravitational lensing event, where the gravity of a foreground object, like a star or planet, briefly focused and amplified a much weaker, distant radio source, making it appear extraordinarily powerful for a short time before fading away. While this is physically possible, the odds of such a perfect alignment creating a signal that so precisely mimics an artificial beacon are astronomically low. The WOW signal remains a tantalizing enigma, a siren call from the depths of space that continues to captivate scientists and the public alike. It is a reminder that in the vast, quiet search for other minds in the cosmos, we have, for one brilliant moment, heard something that defies all easy explanation. It stands as a monument to the possibility that we are not alone, and a humbling testament to the fact that the universe is still capable of producing wonders that leave even the most rational among us reaching for a pen to simply write. While gravity is the force we know best in our daily lives, it's the pull that keeps our feet on the ground and governs the majestic dance of planets around the sun. Yet, when we try to understand it at the most fundamental level, it becomes the most mysterious and stubborn force in the entire cosmos. This mystery lies at the heart of our next question: what is quantum gravity? To appreciate the depth of this puzzle, you have to recognize the great schism at the foundation of modern physics. On one side, we have Einstein's masterpiece, the theory of general relativity. This is the theory of the very large, the theory of the cosmic stage. It describes gravity not as a force in the traditional sense, but as the elegant warping of spacetime itself. A massive object like the Sun creates a dimple in the fabric of the universe, and planets like Earth simply follow the curved geometry of that dimple. This theory is spectacularly successful. It predicts the bending of starlight, the existence of black holes, and even the precise timing of the GPS satellites orbiting our planet. Its equations paint a beautiful, continuous picture of a smooth, flexible universe. Then, on the other side, we have the bizarre and counterintuitive world of quantum mechanics. This is the theory of the very small, governing the realm of atoms and subatomic particles. In this domain, the universe is not smooth and continuous, but grainy and probabilistic. Particles can be in two places at once. They can tunnel through barriers, and they communicate instantaneously through spooky entanglement. The other three fundamental forces, the electromagnetic force, the strong nuclear force that HOLDS Chinese letter TOGTHER, and the weak nuclear force responsible for radioactive decay, are all described by quantum theories with incredible precision. They are transmitted by tiny, discrete packets of energy called quanta. For instance, the photon is the quantum or force carrier for the electromagnetic force. But gravity stands completely apart. We have no quantum theory for it, and when we try to force general relativity and quantum mechanics to talk to each other, the result is mathematical chaos. Their equations are written in different languages and based on fundamentally different rules about how reality works. The core of the conflict lies in this graininess. Quantum theory says that everything, including the fabric of space, should be made of tiny, discrete packets, but general relativity treats space as a smooth, continuous canvas. When you try to describe the intense, microscopic curvature of spacetime at the center of a black hole, or at the moment of the Big Bang places where gravity is incredibly strong and volumes are incredibly small, the equations of general relativity break down. They produce nonsensical answers, predicting points of infinite density known as singularities, which are essentially physics' way of saying, "I give up." To truly understand the birth of the universe or the final fate of matter inside a black hole, we need a theory that can describe gravity under these extreme conditions. We need a theory of quantum gravity, a framework that tells us what the quantum of gravity is, the hypothesized graviton, and how it operates. This is not just an academic exercise. It is the essential next step in our quest for a theory of everything, a single set of equations that can describe all physical phenomena, from the whirl of galaxies to the spin of an electron. The most famous and ambitious candidate for this unified theory is string theory. Imagine that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating strings or loops. What we perceive as different particles, an electron, a quark, a photon, are actually just different notes, different vibrational patterns, played on these fundamental strings. In this symphony of the cosmos, the graviton would be one particular vibrational mode, seamlessly unifying gravity with the other forces. The appeal of string theory is profound. It naturally incorporates gravity and has the mathematical elegance of a grand, universal composition. However, this elegance comes at a staggering cost. For the equations to work, string theory requires that the universe has many more dimensions than the 4 we experience, up to 10 or 11 in some versions. The idea is that these extra dimensions are curled up, or compactified, into a space so infinitesimally small that we are completely unaware of them. like a garden hose that looks like a one-dimensional line from a distance, but is actually a two-dimensional surface curled into a cylinder. The challenge and the major criticism of string theory is that it has so far made no testable predictions that can be verified in a laboratory. The energy levels required to see these strings or probe the extra dimensions are far, far beyond the reach of any particle accelerator we could ever build, leading some skeptics to question whether it is even a scientific theory at all, or a beautiful piece of abstract mathematics. A very different, and in some ways more austere, approach is loop quantum gravity. If string theory tries to rewrite all of physics by changing the nature of particles, loop quantum gravity tries to quantize the stage itself, the fabric of spacetime. This theory proposes that space is not smooth and continuous, but is actually woven from a network of finite, tiny loops. Think of the fabric of the universe as a tapestry made of individual, interconnected threads. These loops are incredibly small at the Planck scale, which is about 10 to the power of negative 35 meters. At this scale, space is granular, and you cannot divide it further. It is made of discrete atoms of space. This has a breathtaking consequence. It banishes the singularities that plague general relativity. There is no such thing as an infinitely dense point in a black hole or at the Big Bang, because you simply run out of space to compress. Instead, loop quantum gravity suggests a big bounce, where a previous universe collapsed to an extremely high density, but not an infinite one, and then rebounded into our own expanding cosmos. While this theory is less ambitious than string theory in that it focuses primarily on quantizing gravity rather than unifying all forces, it is potentially more testable. Some versions predict subtle modifications to the cosmic microwave background radiation or to the behavior of light from distant gamma-ray bursts, offering faint glimmers of hope for future experimental verification. The immense difficulty in testing these ideas highlights the monumental challenge of probing quantum gravity. We are trying to observe effects that become significant at the Planck scale, a realm of such minuscule size and incredible energy that it is completely inaccessible to our current technology. It would require a particle accelerator the size of our entire solar system to reach the necessary energies to directly produce a graviton or see the granularity of space. So, scientists have to be incredibly clever, looking for indirect signatures in the data we can collect. They scour the cosmic microwave background for imprints of the early universe, search for anomalies in the light from distant astrophysical objects, and even use tabletop experiments with supercooled materials to look for tiny deviations from the predictions of classical gravity. The search for quantum gravity is perhaps the most profound and difficult endeavor in all of modern physics. It is a journey into a realm where our current concepts of space, time, and matter melt away, forcing us to invent an entirely new language to describe reality. It is the final frontier of fundamental physics, and its resolution will undoubtedly rewrite our understanding of the universe in ways we can barely imagine. This extraordinary fine-tuning, this seemingly miraculous calibration of the cosmos, brings us face to face with a concept that is as profound as it is controversial: the anthropic principle. The premise is disarmingly simple yet deeply unsettling. Consider the fundamental forces that govern reality. The strength of the force that binds atomic nuclei, known as the strong nuclear force, is set with unbelievable precision. If it were just a few percent stronger, the universe would have fused all its hydrogen into helium in the first few minutes after the Big Bang, leaving no fuel for stars to shine for billions of years. There would be no water, no stable suns, no long-lasting cosmic engines to power life. If it were slightly weaker, complex atomic nuclei could never form at all. Deuterium, a crucial stepping stone in stellar fusion, would be unstable, and the universe would consist of nothing but hydrogen, a featureless sea of the simplest element. The cosmos would be chemically inert, incapable of producing the complex molecules that life requires. Now, shift your focus to gravity. The force that holds planets in their orbits and shapes galaxies seems robust, but its specific strength is also a delicate compromise. If the gravitational constant were a little bit stronger, stars would burn through their nuclear fuel at a ferocious rate, collapsing into black holes long before planetary systems could form or life could emerge. The universe would be a violent, short-lived place. If gravity were somewhat weaker, it would never be able to overcome the initial expansion of the Big Bang to clump matter into galaxies and stars in the first place. The cosmic clouds of gas and dust would simply drift apart forever, a cold, dark, and sterile mist. Even the mass of a humble electron is fine-tuned. If it were different by a minuscule amount, the chemistry of carbon, the backbone of life as we know it, would fail. Carbon would not be produced in the hearts of stars in the quantities needed to seed the universe, and the intricate dance of molecular bonding that allows for DNA and proteins would be impossible. The list goes on and on, from the cosmological constant to the ratio of the electromagnetic force to gravity. Dozens of knobs on the cosmic control panel that are all set to values that allow for a universe that is old, structured, and hospitable to life. Faced with this overwhelming evidence of cosmic fine-tuning, scientists and philosophers have proposed several powerful, yet radically different, explanations. The first and most intuitive for many is the teleological argument, the idea that the universe appears designed because it is designed. In this view, the precise calibration of the physical constants is the fingerprint of a creator, a divine intelligence that set the parameters with the explicit purpose of allowing life and consciousness to flourish. This perspective offers a satisfying answer to the why, providing a narrative of intentionality and purpose behind the existence of a life-permitting cosmos. It resolves the unease of a seemingly miraculous coincidence by positing a miracle worker. A second and profoundly influential scientific response emerges from the concept of the multiverse. If our universe is just one bubble in an infinite, frothing ocean of universes, each with its own randomly selected set of physical laws and constants, then the mystery of fine-tuning evaporates. In an infinite multiverse, every possible combination of physical parameters will be realized somewhere. The vast, overwhelming majority of these universes will be stillborn or barren. They will have gravity too strong or electromagnetism too weak, or a cosmological constant so large that space rips itself apart instantly. But in an unimaginably vast ensemble of universes, a tiny, tiny fraction will, purely by chance, have all the knobs set just right. And, of course, we can only find ourselves in one of those rare, habitable bubbles. We shouldn't be surprised to observe a universe that permits our existence. It is the only kind of universe we could observe. The multiverse turns a miracle into a statistical inevitability, a cosmic version of a lottery winner being astonished they won, forgetting that someone had to win, and they are the one holding the ticket. A third, more minimalist interpretation is known as the weak anthropic principle. This is not an explanation for why the universe is fine-tuned, but rather a logical statement about our observations. It argues that we must take into account the fact that our existence as observers imposes a selection effect on the data we can collect. We are not seeing a randomly selected universe from all possible universes. We are seeing the one particular universe that has the properties necessary for our existence. If the constants were different, we wouldn't be here to notice. This is not so much an answer as a reminder of the boundaries of our inquiry. It cautions against drawing grandiose conclusions from a sample size of one. The weak anthropic principle says, in effect, that the universe appears finely tuned for life for the simple and trivial reason that if it weren't, we wouldn't be having this conversation. Each of these responses carries its own weight and its own set of challenges. The design argument often sits outside the testable realm of science, residing in the domain of metaphysics and faith. The multiverse theory, while a compelling and popular solution within theoretical physics, currently lacks direct observational evidence. It is a powerful inference from theories like inflation, but it remains, for now, unproven. And the weak anthropic principle, while logically sound, can feel like a conversation stopper, a way of dismissing a profound mystery rather than engaging with it. The debate over cosmic fine-tuning ultimately forces us to confront the very nature of reality and our place within it. Are we the intended product of a conscious creation, the incredibly lucky winners of a cosmic lottery, or simply the inevitable observers in a reality that must, by logical necessity, appear tailored to our needs? The answer to this question remains one of the most profound and unresolved at the intersection of science, philosophy, and human curiosity. Sometimes, the biggest mysteries in space are not found in the distant cosmos, but right here in our own celestial backyard, hidden in the subtle, unexpected behavior of the very probes we send out to explore. A perfect example of this is the long-standing puzzle known as the Pioneer Anomaly. In the early 1970s, NASA launched two intrepid robotic explorers, Pioneer 10 and Pioneer 11, on trajectories that would take them past Jupiter and Saturn, and then on a one-way trip out of the solar system. For decades, as these spacecraft journeyed into the deep, cold expanse beyond the orbit of Pluto, scientists back on Earth meticulously tracked their positions using the Doppler shift of their radio signals. By monitoring the tiny changes in the frequency of these signals, they could calculate the spacecraft's velocity and distance with incredible precision. Everything seemed to be proceeding according to the well-established laws of orbital mechanics and gravity, until researchers noticed something bizarre. Both Pioneer 10 and Pioneer 11 were not quite where they were supposed to be. They were experiencing a constant, minuscule, but undeniable acceleration back toward the sun. This was completely unexpected. The primary force acting on the probes at that distance should have been the sun's gravity, which was slowing them down as they climbed out of the solar system's gravitational well. Instead, they were slowing down just a tiny bit more than predicted. It was as if an invisible hand was ever so gently applying the brakes, tugging the spacecraft sunward with a force about 10 billion times weaker than the gravity we feel here on Earth's surface. While incredibly small, this anomalous acceleration was persistent, and it defied all immediate explanation for over 2 decades, creating a tantalizing mystery at the fringes of our knowledge. The first and most exciting possibility that crossed everyone's mind was that this was a sign of new physics. Could our understanding of gravity itself be incomplete? Perhaps Einstein's theory of general relativity needed a minor adjustment for the weak gravity environment of the outer solar system. Some theorists propose the existence of unseen, diffuse dark matter in our solar system, exerting an extra gravitational pull. Others speculated about hypothetical modifications to the law of gravity itself. suggesting that gravity might behave differently over very large scales than our current models predict. The Pioneer anomaly became a rallying point for physicists questioning the foundations of our cosmic rulebook, a tiny data point with potentially universe-altering implications. The mystery deepened because this effect seemed unique to the Pioneer probes. Other distant spacecraft, like the Voyagers, did not show the same clear anomaly. This discrepancy, however, turned out to be a crucial clue, pointing not toward new physics, but toward the spacecraft themselves. The Voyager probes were three-axis stabilized, meaning they could rotate and adjust their orientation, much like a car being steered down a highway. The Pioneer spacecraft, by contrast, were spin-stabilized, rotating like a perfectly thrown football to maintain a stable orientation in the vacuum of space. This difference in design and operation would ultimately hold the key to the puzzle. The most widely accepted solution to the Pioneer anomaly is a masterclass in engineering detective work and demonstrates that the most prosaic explanations are often the correct ones, even if they are incredibly difficult to prove. The leading culprit is a tiny, anisotropic thermal radiation force. In simpler terms, it's heat. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, or RT. These nuclear power sources produced a significant amount of waste heat as a byproduct of generating electricity. The spacecraft also had electronics compartments that generated their own heat. This heat had to be radiated away into space to prevent the probes from overheating. Crucially, this radiation of heat is not just a temperature change. It carries momentum. Every photon of infrared light emitted from the spacecraft gives it a tiny, minuscule push in the opposite direction. Now, if the spacecraft were a perfectly symmetrical sphere radiating heat equally in all directions, these pushes would all cancel out, resulting in no net force. But the Pioneer probes were not symmetrical. Their large main antenna dish acted as a kind of shield, reflecting a significant portion of the heat radiation from the RTGs and electronics back toward the front of the spacecraft. This created a tiny imbalance. Slightly more heat was being radiated from the warm backside of the probe toward its cooler front, where the main antenna was pointed. This resulted in a net force pushing against the direction of the antenna, which, for a spacecraft heading out of the solar system, is a direction pointing back toward the sun. Confirming this hypothesis required an extraordinary effort. Decades after the probes were launched, a team of scientists led by Slava Turishev embarked on a digital archaeological mission. They had to recover and reprocess decades-old telemetry and engineering data, some of it stored on outdated magnetic tapes and in old, poorly documented formats. They even used data from scale models of the Pioneer spacecraft to create a detailed thermal model, simulating exactly how heat flowed and radiated from every surface. The painstaking analysis showed that the anisotropic heat radiation could account for the vast majority of the observed anomalous acceleration. It was not a flaw in gravity, but a subtle and previously unaccounted for side effect of the spacecraft's own design and operation. The case appeared to be closed, a triumph of meticulous scientific and engineering sleuthing over the allure of exotic new physics. Yet a whisper of the original mystery persists. Even after the most sophisticated thermal models were applied, some analyses suggested a tiny, residual anomaly might still remain, an acceleration so small it sits right on the edge of detectability, a potential ghost in the machine that the thermal explanation cannot fully extinguish. This lingering uncertainty, however small, is why the Pioneer anomaly remains so important. It serves as a profound lesson in humility and precision. It reminds us that when we push the boundaries of measurement to such incredible extremes, we must account for every possible effect, no matter how trivial it may seem. The spacecraft itself becomes part of the experiment, and its own mundane properties, its paint, its power source, its shape, can generate signals that mimic the discovery of new fundamental laws. The story of the Pioneer anomaly is a cautionary tale for future missions, especially as we plan to send even more precise probes into the depths of space. It forces us to ask whether we truly, completely understand how all the forces, including the gentle push of photons, behave on the smallest scales in the hard vacuum of interplanetary space. While the case is largely considered solved, that faint, unresolved whisper ensures that this particular cosmic detective story may not have delivered its final verdict just yet. Leaving behind the subtle tugs on our own spacecraft, we encounter a visitor that arrived unannounced from the depths of interstellar space, an object that challenged our very definitions of what is natural and what might be possible. In October 2017, astronomers at the University of Hawaii made an extraordinary discovery. Using the Pan-STARRS telescope, they spotted a faint point of light moving at a blistering speed, one so high it could not possibly be bound by the sun's gravity. This was not a comet or asteroid from our own solar system. It was the first confirmed interstellar object ever observed, a cosmic tourist just passing through. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Its trajectory was a stark, hyperbolic arc. It had fallen from above the plane of our solar system, swung around the sun, and was now racing away, never to return. The race was on to learn everything we could about this mysterious visitor in the brief window before it faded from view. The first surprise was its shape. Based on the dramatic changes in its brightness as it tumbled through space, astronomers inferred that Oumuamua was not a roughly spherical object like most asteroids or comets. Instead, it was profoundly elongated. Its brightness varied by a factor of 10 as it rotated, suggesting an object that was at least 5 to 10 times longer than it was wide. Some models even suggested a pancake-like flatness. Imagine a cigar or a thick disc tumbling end over end through the void. This was unlike any natural object we had ever seen in our own solar system. But the greatest mystery was yet to come. As Oumuamua continued on its outbound journey, astronomers tracking its position noticed something deeply puzzling. Its path could not be explained by gravity alone. After being slung around the sun, it should have been gradually slowing down as our star's gravity pulled back on it. Instead, it was speeding up. It was experiencing a tiny but clear and persistent non-gravitational acceleration. This is the kind of behavior we see in comets. As a comet approaches the sun and heats up, ices on its surface turn directly into gas in a process called outgassing. This jetting material acts like a gentle rocket engine, giving the comet a push. The critical clue with comets is that this outgassing also releases dust and gas, forming a visible coma and a magnificent tail. Scientists pointed every telescope they could at Oumuamua, searching for this telltale signature. They found nothing. No coma, no tail, no trail of dust. It was as if an invisible engine was pushing it. The scientific community scrambled for explanations. The leading natural hypothesis centers on the outgassing of something far more exotic than the water ice we see in typical comets. One compelling idea is that Oumuamua was composed largely of molecular hydrogen ice. Hydrogen is the most common element in the universe, but it's incredibly difficult to freeze, requiring temperatures only found in the densest, coldest molecular clouds. If Oumuamua formed in such a cloud, it could have accumulated as a hydrogen iceberg. As it passed close to our sun, the warming would have caused the solid hydrogen to sublimate directly into gas. Because hydrogen gas is invisible to our telescopes and doesn't drag dust with it, this could explain both the non-gravitational acceleration and the complete lack of a visible coma or tail. Another possibility is that it was a chunk of solid nitrogen ice, similar to the surface of Pluto. As the nitrogen sublimated, it would have provided the thrust without producing the dusty debris of a traditional comet. These are clever and plausible natural explanations, but they require Oumuamua to be made of materials that are quite rare in the forms we're familiar with, pushing the boundaries of what we consider a typical planetary building block. The object's strange combination of properties, its extreme shape, its mysterious acceleration, and its utter lack of visible activity inevitably led to a more speculative but scientifically articulated hypothesis. Could Oumuamua be an artifact of an alien technology? This suggestion was most famously put forward by Harvard astronomer Avi Loeb. He proposed that the acceleration could be explained by solar radiation pressure. Sunlight itself exerts a tiny force, and if Oumuamua were extremely thin and light, a solar sail, in essence, the pressure from photons from the sun could have provided the push we observed. A solar sail is a proposed technology for interstellar travel, where a vast, incredibly thin sheet uses starlight for propulsion, needing no fuel. In this scenario, Oumuamua could have been a piece of a discarded solar sail, a derelict probe, or even an active piece of equipment drifting through the galaxy. Loeb argued that we should seriously consider this possibility because it matches the observational data without requiring exotic ices that we have never directly observed in such a form. The vast majority of the scientific community remains skeptical of the artificial origin theory, favoring natural explanations, however unusual. They point out that Oumuamua's trajectory showed no signs of intelligent guidance, no course corrections, and its appearance, while strange, is not impossible for a natural object. It could be a fragment from a planet torn apart by its star, or a piece of debris from another solar system's version of our Kuiper belt, processed by billions of years of cosmic radiation into its peculiar shape. The true significance of Oumuamua may not be in any single answer, but in the door it opened. Its visit was a revelation, showing us that interstellar objects are passing through our solar system with some frequency. Before its discovery, our models suggested such visitors would be rare. Now, we suspect there could be thousands within the orbit of Neptune at any given time. We simply lack the technology to see them. Oumuamua was a trailblazer, and its legacy is a new field of astronomy dedicated to hunting for and studying these interstellar travelers. Future telescopes, like the Vera C. Rubin Observatory, are expected to find many more, allowing us to build a statistical understanding of what these cosmic nomads are like. Was Oumuamua a bizarre hydrogen iceberg, a chunk of exotic nitrogen, or something else entirely? Its fleeting visit left us with more questions than answers, a perfect emblem of the scientific process. It reminds us that the universe is under no obligation to conform to our expectations, and that sometimes the most profound mysteries arrive quietly, without warning, on a trajectory from the great unknown. This framework for thinking about alien intelligence, developed by the Soviet astronomer Nikolai Kardashev in the 1960s, gives us a tangible way to measure the truly awesome potential of a civilization. Instead of guessing at their biology or philosophy, the Kardashev scale focuses on something we can actually quantify: energy. How much power does a society command? According to this scale, a civilization's technological maturity can be ranked by its ability to harness and utilize the energy resources available to it. A Type 1 civilization has achieved mastery over its home planet. This doesn't just mean having a global power grid. It means they can control weather patterns, prevent natural disasters like earthquakes and volcanic eruptions, and harness every bit of energy that their world receives, from the heat of its core to the sunlight that bathes its surface. Humanity, for all our satellites and smartphones, doesn't even register as a full Type 1 yet. By some estimates, we are currently at Type 0.7, still reliant on burning dead plants and animals for the bulk of our energy needs, with only fledgling control over our planetary systems. The leap to a Type 2 civilization is where the scale truly enters the realm of science fiction, yet it remains grounded in known physics. A Type 2 civilization would have outgrown the limited energy budget of a single planet, and would instead capture the total energy output of its home star. The most famous theoretical construct for this is the Dyson sphere. Imagine a vast, intricate swarm of solar collecting satellites, not just a solid shell, but millions or billions of individual units encircling the star in a tight formation, absorbing nearly all of its light and beaming that colossal energy back to the home world or other colonies. The power available here is almost unimaginable quadrillions of times more than what our entire global civilization consumes today. With that kind of energy, a species could reshape solar systems, move planets, or even initiate stellar engineering projects to extend the life of their star. The waste heat from such an immense structure would be detectable across interstellar distances as an excess of infrared radiation. Our telescopes have scanned the skies for just such a signature, looking for stars that seem oddly dim in visible light, but glow brightly in the infrared. So far, we have found candidates that are intriguing, like the famously flickering star Tabby's star, but all have had plausible natural explanations, such as clouds of dust or swarms of comets. No definitive evidence of a Dyson sphere has ever been confirmed. A Type 3 civilization transcends the stellar scale altogether, becoming a truly galactic entity. This is a culture that has colonized, or at the very least harnessed the energy from millions upon millions of star systems across its entire galaxy. Their energy consumption would be on a scale that defies human comprehension, equivalent to the output of hundreds of billions of suns. Their activities might be visible from across the universe. Perhaps they would communicate using neutrinos or gravitational waves, technologies completely invisible to our current detectors. They might even be able to manipulate the fabric of spacetime itself, employing wormholes for instantaneous travel, or tapping into the energy of the supermassive black hole at the galactic center. The astronomer Carl Sagan once speculated that a truly advanced civilization might not even be recognizable as a physical entity. It might have transcended biology entirely, existing as a vast, collective consciousness distributed across the stars, its thoughts and communications occurring in realms and mediums we cannot perceive. This brings us to the haunting, central question raised by the scale. If such civilizations are possible, where are they? The silence of the cosmos is deafening. We see no great swarms of stars being systematically dimmed, no galaxies shining with the unmistakable infrared signature of a civilization using all its starlight. This profound absence suggests several unsettling possibilities. Perhaps the most optimistic is that such immense, energy-intensive civilizations are simply not sustainable. Maybe the transition from Type 2 to Type 3 is the universe's ultimate filter. The energy and resource demands of a galactic empire could inevitably lead to internal conflict, catastrophic collapse, or a deliberate choice to abandon physical expansion in favor of a more subtle, introspective existence. Another possibility is that our search methods are fundamentally naive. We are looking for signatures based on our own primitive understanding of physics and engineering. A civilization that is even 1,000 years more advanced than us might use technologies that are as incomprehensible to us as a smartphone would be to a medieval peasant. Their mega structures might not be solid objects, but dynamic fields of force. Their energy might not be radiated as wasteful heat, but recycled with 100% efficiency, leaving no trace for our telescopes to find. The most humbling thought of all is that Type 2 and 3 civilizations might be all around us, but their activities are simply on a scale too vast or too subtle for us to notice. We are like ants living in a single blade of grass in a vast national park, completely unaware of the park rangers, the hikers, and the complex infrastructure that manages the entire environment. The rangers are not hiding from the ants. They are simply operating on a different level of reality, their actions and purposes completely beyond the ants' capacity to understand. The Kardashev scale, therefore, is more than just a classification system. It is a mirror that reflects our own technological infancy and a challenge to our imagination. It forces us to ask not just what is possible, but what is probable, and to wonder if the ultimate fate of intelligence in the universe is to blaze across the galaxy in a visible, energetic firestorm, or to fade into a state of such perfect, efficient harmony with the cosmos that it becomes indistinguishable from nature itself. But just when we think we have a firm grasp on the cosmic expansion, a stubborn and persistent crack appears in our understanding. A puzzle that has grown from a curious anomaly into a full-blown crisis in cosmology. This is the Hubble tension, a problem that pits the ancient universe against the modern cosmos, and it suggests our picture of cosmic evolution might be missing a crucial piece. The heart of the issue lies in measuring a single, fundamental number, the Hubble constant. This is the current rate of the universe's expansion, telling us how fast galaxies are receding from us at any given distance. Think of it as the current speed limit on the cosmic highway. For decades, astronomers have pursued two distinct and supposedly reliable roads to measure this speed. The first road looks back to the very beginning, to the afterglow of the Big Bang itself. By studying the detailed patterns in the cosmic microwave background with exquisite precision, satellites like Planck can essentially calculate what the expansion rate should be today, based on our well-tested model of the early universe, known as the lambda cold dark matter model. This method works by measuring the size of the primordial sound waves imprinted on the CMB, which act as a standard ruler. The observed angular size of these ripples on the sky, combined with our knowledge of the universe's composition of dark matter and dark energy, allows us to run the cosmic movie forward and predict the current expansion rate. This method gives us a very precise value, around 67.4 kilometers per second per megaparsec. This means that for every additional megaparsec of distance, a distance of about 3.3 million light-years, a galaxy is moving away from us 67.4 kilometers per second faster. The second road to measuring the Hubble constant is more direct. It measures the expansion rate as we see it now in our local universe. This is a cosmic distance ladder approach. You start by measuring distances to nearby stars using parallax, the same way your eyes gauge distance by looking at an object from slightly different angles. You then use these well-understood stars to calibrate the brightness of more distant stars, like Cepheid variables, which pulse at a rate directly related to their true brightness. By knowing how bright these Cepheid stars truly are, and measuring how dim they appear from Earth, astronomers can calculate their distance with high confidence. These Cepheids, in turn, are used to calibrate the ultimate cosmic distance markers, Type 1a supernova. These stellar explosions are so uniform in their peak brightness that they are known as standard candles. When one goes off in a distant galaxy, we know its true luminosity, so by measuring its apparent brightness, we can determine the distance to that galaxy with remarkable accuracy. By combining these distance measurements with the redshifts of the same galaxies which tell us how fast they are moving away from us, we get a direct measurement of the current expansion rate. Teams using this method, most notably the SOES collaboration led by Nobel laureate Adam Rees, have consistently found a higher value, around 73 kilometers per second per megaparsec. Now, a small discrepancy between two complex measurements might be expected, something that could be brushed aside as a minor calibration error or statistical fluke. But the Hubble tension is not small. The difference between 67 and 73 is not just a minor gap. It is a chasm that represents a disagreement of about 9%. Even more importantly, as both methods have been refined with more data and better technology, the error bars on each measurement have shrunk significantly. They have become so precise that the chance this discrepancy is just a statistical accident is now vanishingly small, less than 1 in a million. The two most trusted methods in all of cosmology are now giving us two different, mutually exclusive answers for the current expansion rate of the universe. It's as if you used two different, impeccably calibrated stopwatches to time the same race, and one confidently told you the winner finished in 10 seconds flat, while the other, with equal confidence, declared it was 11 seconds. Both cannot be right. This is the Hubble tension, and it signals that something in our standard model of cosmology is fundamentally amiss. So, what could be causing this profound disagreement? The most exciting possibility is that it's a direct hint of new physics, a clue that our understanding of the universe's ingredients or behavior is incomplete. One compelling line of thought points to the early universe. Perhaps there was a brief, early phase of extra rapid expansion, driven by a new form of energy that we haven't accounted for. This could have subtly altered the conditions imprinted on the cosmic microwave background, which would, in turn, throw off the prediction for the present-day expansion rate. Some theorists suggest this could be connected to early dark energy, a transient field that existed for a short time after the Big Bang, providing an extra push to the expansion before fading away. This would change the sound horizon measured by the Planck satellite, making the early universe prediction for the Hubble constant lower, while leaving the local distance ladder measurement unaffected, perfectly creating the tension we observe. Another fascinating idea involves a potential interaction between dark matter and dark energy. In our standard model, these two components are treated as separate and non-interacting. But what if they can exchange energy? A slow decay of dark matter into dark energy over cosmic history would have changed the expansion rate over time in a way that our simple models don't capture, creating a divergence between the early and late time measurements. Alternatively, the issue might lie with the very nature of dark energy itself. What if it isn't a constant force, as Einstein's cosmological constant suggests, but a dynamic field that has been evolving? If the strength of dark energy has been increasing over time, it would have caused a more recent speed up in expansion, making the local universe appear to be expanding faster than the early universe data would predict. There are even more exotic proposals, such as the existence of a new type of relativistic particle that flooded the early universe, like a sterile neutrino, which would have changed the timing of when matter and radiation decoupled, again tweaking the CMB-based prediction. Or on a more profound level, what if the Hubble tension is a sign that our universe is not as uniform as we think? The assumption of homogeneity, that the universe looks the same in every direction on large scales, is a cornerstone of cosmology. But if we happen to be living in a local underdensity, a cosmic void that is expanding slightly faster than the average, it could make our local measurements of the Hubble constant appear artificially high. While this possibility exists, most detailed studies of large-scale structure suggest such a vast void is unlikely. The Hubble tension, therefore, is not just a technical disagreement about a number. It is a direct challenge, a cosmic crossroad forcing cosmologists to question their most fundamental assumptions. It is the most significant hint we have that our otherwise incredibly successful model of the universe is missing a vital ingredient, a hidden actor in the cosmic drama whose identity remains one of the most active and thrilling pursuits in modern science. As we peer into the farthest reaches of our own solar system, past the familiar orbits of Neptune and Pluto, we find a gravitational ghost hiding in the dark, a hypothetical world whose existence is inferred not by the light it reflects, but by the subtle, coordinated dance of much smaller, icy bodies. This is the mystery of Planet 9. The story begins not with a telescope sighting, but with a pattern in the data, a celestial clue discovered by astronomers Konstantin Batygin and Mike Brown at Caltech in 2016. They were studying the orbits of a group of small, icy objects in the Kuiper Belt, the vast, donut-shaped region of debris beyond Neptune. These aren't your typical Kuiper Belt objects that orbit in roughly the same plane as the major planets. These are extreme trans-Neptunian objects, or ETIMNOs, with orbits that are highly elliptical, tilted dramatically out of the solar system's plane, and, most intriguingly, clustered together in a way that defies random chance. It's as if you were watching a flock of birds flying in a seemingly random sky, and then you noticed that all of them, at the farthest point of their flight, make a sharp turn in the same direction. This orbital alignment is the primary clue, and the simplest explanation is that the gravity of a single massive and as yet unseen planet is shepherding them, herding their orbits into this peculiar configuration. The hypothetical planet needed to orchestrate this cosmic dance must be formidable. Current models suggest a world 5 to 10 times the mass of Earth, placing it in the category of a super-Earth or a mini-Neptune, a type of planet that is incredibly common around other stars but conspicuously absent from our own inner solar system. Its orbit would be colossal, stretching perhaps 400 to 800 times the distance from the Earth to the Sun. At such a distance, a single orbit around the Sun could take anywhere from 10,000 to 20,000 years to complete. This enormous orbital period and its incredible distance from the Sun are precisely why it has eluded detection for so long. A planet this far out receives virtually no sunlight, making it incredibly faint, and its motion across the sky would be glacially slow, requiring painstaking surveys to spot its subtle movement against the background stars over months or even years. The search is on, using the world's most powerful telescopes, like the Subaru telescope in Hawaii, to scan vast swaths of the sky, looking for that one faint, moving pinprick of light that could confirm a new world in our own cosmic backyard. It is a monumental game of hide and seek, played on a canvas that spans billions of miles. If Planet 9 is real, its very existence would force us to rewrite the history of our solar system. How did such a large world end up in such a distant, eccentric orbit? There are two leading theories for its origin, each with dramatic implications. The first is that Planet 9 is a primordial world, a genuine native of our solar system that formed much closer to the Sun, alongside the other planets. In the chaotic early days of the solar system, gravitational interactions with the giant planets, particularly Jupiter and Saturn, could have flung this nascent world on a long, looping orbit, scattering it to the outer darkness where it has resided ever since. This would mean our solar system did, in fact, form a super-Earth, but its destiny was to be exiled, becoming a solitary sentinel in the frigid outskirts. The second, even more captivating possibility is that Planet 9 is an interstellar interloper, a captured exoplanet. In this scenario, our Sun, in its youth, was part of a dense cluster of stars being born together. During this time, it could have gravitationally snatched a rogue planet that was drifting freely through space, or stolen it from a neighboring star system. If true, Planet 9 would be the first captured exoplanet we have ever identified, a permanent souvenir from another sun, offering us an unprecedented opportunity to study a world from a different stellar nursery without ever leaving our own solar system. Finding Planet 9, or definitively ruling it out, is therefore about much more than just tallying another planet. It is a crucial test for our models of planetary system formation and evolution. Its existence would elegantly solve the puzzle of the clustered Etino orbits and potentially explain other solar system mysteries, like the unusual tilt of the Sun's rotational axis. It would confirm that dynamical processes can fling a giant world to the very fringes of a star's gravitational influence, a finding that would have profound implications for how we interpret the wide orbit planets we are now discovering around other stars. Conversely, if years of dedicated searching ultimately prove that Planet 9 does not exist, the mystery of the clustered Kuiper Belt object orbits deepens considerably. Astronomers would be forced to consider alternative and potentially more revolutionary explanations. Perhaps the collective gravity of a large yet undiscovered disk of smaller icy objects is responsible for the shepherding effect. Or, in the most mind-bending scenario, the orbital anomalies could be a signature of something entirely different, such as a primordial black hole, a relic from the Big Bang with the mass of a planet, but only the size of a grapefruit, whose immense gravitational pull would mimic that of a world. This tiny, dark object would be nearly impossible to detect directly, and its presence would open a completely new and unexpected chapter in solar system physics. The quest for Planet 9 is far more than a planetary hunt. It is a fundamental investigation into the architecture and history of our celestial home, a reminder that even in our own familiar solar system, the greatest discoveries may still be waiting in the dark. While we often picture our galaxy as a relatively flat, spinning disk of stars, recent discoveries have revealed that it is also home to colossal, ghostly structures that defy this simple image. Projecting tens of thousands of light years above and below the galactic plane are two immense spheres of extremely hot gas and high-energy radiation, known collectively as the Fermi bubbles. These are not made of stars, but are vast, balloon-like lobes of energy, each one towering 25,000 light years into space. If you could see them in the night sky, They would stretch from the constellation Virgo all the way to Grus, the crane, covering over half of the visible heavens. For a long time, these bubbles remained completely hidden from us, their faint glow washed out by the brilliant backdrop of the Milky Way's central band. They were only discovered in 2010, not by an optical telescope, but by NASA Fermi Gamma Ray Space Telescope, which could see the universe in the most energetic form of light. The bubbles are essentially two of the largest individual structures we have ever found, and they are emanating from the very heart of our own galactic home, a silent and monumental testament to a cataclysm that occurred in our cosmic backyard. The most compelling and dramatic explanation for the creation of the Fermi bubbles points directly to the sleeping giant at the center of our galaxy, the supermassive black hole known as Sagittarius A. While it is relatively quiet today, astronomers suspect that its past was far more violent. The leading theory is that several million years ago, Sagittarius A experienced a massive feeding frenzy. As vast amounts of gas, dust, and perhaps even entire stars spiraled into its gravitational clutches, the black hole's powerful magnetic fields and intense radiation pressure channeled some of this infalling material into two colossal jets, erupting from its poles at nearly the speed of light. These jets, composed of ultra-hot plasma, would have blasted perpendicularly out of the galactic disk, punching through the interstellar medium and inflating these gigantic, bipolar bubbles like a cosmic bellows. This kind of eruption is known as an active galactic nucleus event, and while we see these powerful jets in distant galaxies, the Fermi bubbles are the first clear evidence that our own Milky Way has undergone a similar, if somewhat smaller, outburst in its recent history. The event would have been brief on cosmic timescales, perhaps lasting only 10 or 20,000 years, but its impact was permanent, sculpting the very structure of the galactic halo that surrounds us. However, not all scientists are convinced that our central black hole is solely to blame. A competing and equally fascinating theory suggests that the Fermi bubbles were forged not by a single explosive event, but by a sustained, ferocious period of star formation near the galactic center. In this scenario, the region around Sagittarius experienced a starburst, a frenzy where millions of stars were born in a relatively short period. The most massive of these stars would have lived fast and died young, exploding as supernova in a relentless, coordinated cadence. The combined shock waves and stellar winds from these countless explosions could have created a powerful spherical outflow of energy, a galactic superwind that, over time, inflated the bubbles from the inside out. This theory elegantly explains why the bubbles appear so symmetrical and lack the narrow, focused jet structure often seen in black hole outbursts. It paints a picture of the galactic center as a cosmic engine of creation and destruction, where the collective fury of stellar birth and death can shape the galaxy on a scale that rivals the power of its central black hole. So, how do we choose between a dramatic black hole eruption and a spectacular starburst festival? The key lies in the bubble's detailed structure and composition. Astronomers use powerful X-ray and ultraviolet telescopes to map the temperature, density, and motion of the gas within the bubbles. If the material is streaming outward in a focused, collimated flow, it would strongly support the jet hypothesis. If instead, the gas is more turbulent and shows signs of being heated by countless shock waves from different directions, the starburst model becomes more likely. Recent observations have added another layer of mystery, revealing a hard, defined edge to the bubbles and a subtle substructure of nested shells within them, suggesting there may have been multiple outbursts, a series of energetic pulses rather than one single cataclysmic event. This has led to a compelling synthesis of the two ideas. Perhaps the black hole's activity was triggered by the starburst. As massive stars formed and died, their material could have funneled toward Sagittarius A, providing the fuel it needed to awaken and unleash its own fury, creating a feedback loop of cosmic violence. The Fermi bubbles, therefore, are not just a stunning sight. They are a fossil record of our galaxy's most energetic chapter, a cold case file that astronomers are only now beginning to piece together. Understanding their origin is crucial because it tells us that our seemingly quiet and stable Milky Way has a volatile and dramatic history, and that the forces which shape the most distant, active galaxies are also at work, quietly, in our own celestial neighborhood. And so, we arrive at the final frontier of our cosmic journey, a question so profound it underlies every mystery we have explored. What is the ultimate nature of reality? We have traveled from the singularity of the Big Bang to the event horizon of black holes, from the ghostly pull of dark matter to the silent statistics of the Fermi paradox. Yet, all these inquiries lead us back to this fundamental puzzle. Is the universe fundamentally a collection of tiny, vibrating strings? A holographic projection, a purely mathematical structure, or is the world we perceive merely a sophisticated user interface crafted by our brains? This is not just the 30th question. It is the bedrock upon which all the others rest, a convergence of physics and philosophy that seeks to decipher the very code of existence. One of the most ambitious attempts to answer this comes from string theory, a framework that proposes a radical shift in what we consider fundamental. Forget point-like particles. Imagine that the most basic constituents of reality are inconceivably tiny, vibrating loops or filaments of energy. In this symphony of the cosmos, the different vibrational patterns of these strings give rise to the entire particle zoo: the electron, the quark, the photon, and crucially, the graviton, the hypothesized quantum of gravity. The appeal is breathtaking. A single, elegant entity could unify all forces and matter. However, this elegance demands a staggering price. For the mathematics to work, string theory requires the universe to have not just the 4 dimensions we experience, but 10 or 11. The extra dimensions are theorized to be curled up into a space so minuscule, 1 billion times smaller than an atom, that they are completely hidden from our perception. This leads to the concept of the string theory landscape, a vast, possibly infinite, collection of possible universes, each with different compactified dimensions and therefore different physical laws. In this view, our reality is just one possible configuration in a cosmic library of possibilities, and the ultimate nature of things is a multi-dimensional vibration. An even more mind-bending proposal is the holographic principle, an idea that emerged from wrestling with the black hole information paradox. This principle suggests that our perception of a 3-dimensional universe is an illusion, a hologram. All the information that describes everything within a volume of space, every star, every planet, every person, is actually encoded on a 2-dimensional surface that bounds that volume, like the event horizon of a black hole. Think of the 3-dimensional world you see on a credit card hologram. All its information is stored on the 2-dimensional surface of the card. In a cosmic context, this means the universe we inhabit, with its rich depth and volume, could be a projection from a vast, 2-dimensional shell at the edge of our observable cosmos. Reality, at its most fundamental level, would not be 3-dimensional at all. It would be a kind of pixelated image, with the Planck length setting the ultimate pixel size. This idea forces us to reconsider the very nature of space, suggesting that it is not a fundamental backdrop, but an emergent property, a derivative of information stored elsewhere. Stepping even further into the realm of pure abstraction, we encounter the mathematical universe hypothesis, championed by cosmologist Max Tegmark. This hypothesis proposes that our physical reality isn't just described by mathematics, it is mathematics. More specifically, it is a mathematical structure. In this view, the universe is a set of abstract entities with relations between them, existing in a way that is independent of any human mind. You, the Earth, the galaxy, are not just behaving according to mathematical rules. You are manifestations of those rules. The hypothesis argues that a mathematical structure has an objective, Platonic existence. If this is true, then every consistent mathematical structure exists physically, giving rise to a level 4 multiverse that is vastly larger than the inflationary or many worlds versions. In this ultimate ensemble, every conceivable universe governed by any coherent set of mathematical laws is real. Our particular universe feels concrete and specific to us simply because we are self-aware substructures within one specific, incredibly complex mathematical object. Here, the ultimate nature of reality is not physical substance, but immutable mathematical truth. But what if we are asking the question from the wrong perspective entirely? All these theories, strings, holograms, mathematical structures are attempts by our human brains to model an external world. This leads to a powerful counterpoint from the world of neuroscience and philosophy, the interface theory of perception. Proponents of this view, like cognitive scientist Donald Hoffman, argue that our perceptions are not a window onto objective reality. Instead, they are a species-specific user interface, shaped by evolution not for truth, but for survival. We see solid objects not because things are fundamentally solid, but because perceiving them that way helped our ancestors avoid predators and find mates. Space and time themselves may not be fundamental features of the universe, but simply the desktop of our cognitive operating system, a convenient framework for navigating the world and making fitness-promoting decisions. In this view, asking what reality is really like might be as futile as a computer character asking what the computer's microprocessor is really like. The true underlying reality, whatever it is, could be utterly alien and incomprehensible to our brains, which have evolved to hide this complexity behind a simple, useful dashboard of shapes, colors, and causes. So, where does this leave us in our quest for the ultimate nature of reality? We are faced with a spectrum of possibilities, each with profound implications. If string theory is correct, we live in a universe of hidden dimensions where all physical phenomena are unified through vibration. If the holographic principle is true, our world is a projection, a cosmic illusion with far less information than it appears to have. If the mathematical universe hypothesis holds, then we are living proofs in an abstract, timeless equation. And if the interface theory is accurate, then our entire scientific endeavor is the process of reverse engineering a user interface, not mapping the underlying hardware. These are not merely academic debates. They shape our entire worldview. They determine whether we see consciousness as an emergent property of complex computation, as the holographic and mathematical views might suggest, or as a fundamental property that somehow gives rise to spacetime itself, as some interpretations of quantum mechanics have hinted. This final question therefore ties together the nature of dark energy, the mystery of consciousness, and the puzzle of quantum gravity. It suggests that to understand the cosmos on its largest scales and its smallest, We may first need to understand the nature of the instrument through which we perceive it all, our own mind. The ultimate nature of reality remains the greatest enigma, a silent question hanging over not just the cosmos, but over our very existence as conscious beings within it. From the timeless enigma of what preceded the Big Bang to the unsettling possibility that our reality is a hologram or a mathematical structure, we have ventured to the very edge of human understanding and peered into the abyss. We have grappled with the ghostly presence of dark matter and the repulsive phantom of dark energy, forces that dominate the cosmos yet slip through our fingers. We have contemplated the profound silence of the Fermi paradox and the fleeting, brilliant mystery of signals like, wow. We have stood at the precipice of black holes, where the laws of physics dissolve, and wondered if wormholes could ever stitch the fabric of spacetime itself. We have considered the staggering scale of the Kardashev civilization types and pondered the ultimate nature of our own consciousness. Each of these 30 questions is more than a puzzle. It is a beacon, a declaration that our current map of reality is incomplete, filled with vast, uncharted territories marked only by the words, "Here be dragons." But it is crucial to remember that in science, the dragons are not monsters to be slain, but wonders to be understood. The true value of this journey lies not in the answers we have, which are precious but provisional, but in the relentless, courageous pursuit of the questions themselves. This pursuit is the very engine of science. It is what compels us to build ever larger telescopes, to dig deeper underground in search of elusive particles, to send robotic emissaries to distant worlds, and to scribble equations on blackboards late in the night. Every mystery we have explored represents a frontier where human curiosity is actively pushing back the darkness, piece by tiny piece. This expansion of knowledge is our greatest collective adventure, a story that has been unfolding for millennia and one that is far from over. The cosmos does not give up its secrets easily, and each discovery seems to unveil a deeper, more fundamental layer of mystery. This is not a sign of failure, but a testament to the richness and complexity of the universe we are so privileged to inhabit. So the next time you find yourself under a clear, dark sky, look up. Let your gaze sweep across the star-dusted river of the Milky Way, and remember what you now know. That faint smudge of light is not just a backdrop. It is a dynamic, evolving, and deeply mysterious arena. It is a place where stars are born in colossal nebulae and die in spectacular supernovae, where galaxies flow in immense rivers toward unseen attractors, and where the very laws of physics might be subtly different in other cosmic epochs. You are not just a passive observer. You are a part of this grand story of inquiry, a witness to a moment in time when humanity is just beginning to awaken to the true scale and wonder of the cosmos. The greatest adventures of discovery are not behind us in the history books. They are happening right now, and they are waiting for the next generation of thinkers, dreamers, and explorers to take up the mantle. The universe is asking its most profound questions, and it is inviting you to join the conversation. We would love to hear which of these cosmic mysteries captures your imagination the most. Was it the haunting possibility of a multiverse, the bizarre case of Oumuamua, or the fundamental riddle of quantum gravity? Let us know in the comments below. And if you enjoyed this journey to the edge of knowledge, be sure to subscribe and hit the notification